about 12 kilometers in diameter at nadir, has about 30,000 ecostress pixels in it. And what you can see is there are all kinds of weird patterns in the data. The along track direction is the horizontal, the cross track direction is the vertical. You can see repeating patterns at effectively 8 pixel intervals. You can see diagonal patterns in the data, and you can see vertical stripes that are the result of the non-uniformities in the focal plane. So we have electronics noise, we have spatial noise, and then also alias signals that are coming from other frequency sources within the instrument. So it's very challenging to try to use this instrument for something like SST retrieval. To see how all of this plays out, here I've plotted the power spectra along for observations by a number of instruments on the same day in the along the entrance to the Mediterranean at 36 degrees north. I've separated the spectra on the y-axis just so you can see them better. They all show a decline on approximately the expected slope of the Kolmogorov eddy cascade. And what you notice is that most of them are fairly linear throughout most of their effective spatial range. So MODIS is pretty linear along that range. SLS veers, SGLI going down to 250 meter spatial scale, the same thing. But then you look at ecostress and Landsat, which are the black line and the purple line, and you see there's a fundamental difference. And that is that the spectra level off, which means they're becoming dominated by noise. Ecostress becomes dominated by noise around a 1 kilometer spatial scale. Landsat a little bit later. The extreme drop-off that happens on the right-hand side of the image in Landsat is probably the result of the interpolation. Landsat having a true spatial scale of 100 meters of the actual sensor, but then it's interpolated to 30 meters. And so that drop-off is the result of the interpolation. So the noise actually makes a big difference. We have these high-resolution sensors, but they have noise which is reducing the effective resolution. So where is this all coming from? Here's the temporal noise, NEDT. The brown line at the very top on the left, these are all pre-flight measurements. The brown line is the 12.09 micron channel, which we obviously use for the atmospheric correction. The orange line is the 10.49, which is what we use for primarily retrieving the sea surface temperatures. And then there are other channels on the instrument. And you can see there's a strong temperature dependence. And the comparison is at the very bottom of the graph, you can see the values, the pre-flight values for SLSTR. So the ecostress instrument is way noisier than the best of the SST instruments, and this becomes a fundamental problem. The other issue is that the different detectors in the focal plane have different behaviors. So the right-hand graph shows you the detector by detector patterns of noise, of electronics noise, NEDT, at various temperatures. The black line is at 271K, and what you see in the 10.49 micron channel is that the middle of the focal plane is much noisier than the two ends of the focal plane. And also there's an 8 pixel periodicity in the amplitude of that noise. And so this is likely to lead to funny patterns in the retrieval data at 8 pixel increments. The same thing, the same kind of pattern exists in the 12.09 micron channel. So there are, the electronics NEDT noise has a spatial component to it. And then the spatial noise of the instrument, their individual detectors have different sensitivities. There are 128 pixels in the focal plane, and from pixels approximately 100 to 128, there is an extreme drop-off in the sensitivity of those pixels, and this may come from a vignetting effect. The engineers designed the sunshade for the instrument and assumed that they got the size right, but what they may have done is not made the sunshade wide enough in the scan direction, and so you're getting a vignetting effect, which is blocked. So there's a blockage by the partial blockage by the sunshade. The extreme drop-off on the right-hand side of the focal or the pixels 100 to 128 causes real problems when you start remapping the data, because there's about a 30 pixel overlap in the scans. And so individual pixels that are being remapped could be taken either from the unbiased end of the focal plane, pixels 1 to 130, or from the biased, the strongly negatively biased pixels on the other end of the focal plane. So you end up with alternating hot, cold, hot, cold, hot, cold checkerboards. So we have to get rid of this problem in order to do decent retrievals of SST. So I'm going to talk through a series of different possible approaches to all of this. First, there's the correction approach. And the overall bias correction, we published that in remote sensing earlier this year. That's all done with a series of ISE matchups. And then there's the focal plane non-uniformity, and we're doing that based on the same data that we had for the broad scale calibration. And it's similar to what Jean-Francois and Emmanuel are doing. They've been doing it on a sort of individual, a whole series of individual scenes. We've done it in the individual footprints of our ISE matchups. Then there's a lot of noise that's left, and we've been doing denoising. We've used a long track Fourier notch filters, adaptive notch filters, to try to get rid of some of the remaining noise after the subtraction of the non-uniformity effect. And then we've been trying some wavelet filters in the cross-track direction because the noise in that direction is quasi-periodic, and that's less successful. And then at the resampling, we have found that if you drop the cold end of the focal plane, we get less noise in the final resampled images. So I'll show you what that looks like. So here on the left-hand side is a recalibrated, but without the correction for the focal plane anomaly problem. And there are vertical stripes. Those are the stripes in the along track direction as the horizontal axis. I'm going to show in subsequent slides a series of spectra, one set in the region of the horizontal box on the left-hand image, and that's the along track direction, and then another in the vertically oriented box in the left-hand figure. So the focal plane anomalies that we developed for this particular image are the middle image, and that is subtracted from the uncorrected image to get the corrected image, and it removes an awful lot of the really obvious noise. There's stuff remaining, but it looks a lot better. The problem is that there's quite a lot of remaining noise. So here are spectra in that the along track direction on the upper panel, and in the cross track direction in the lower panel. The black lines are before correction. The red lines are after the non-uniformity correction. And what you can see is that on the upper panel, there's a 9 kilometer periodicity, which is a 128 pixel pattern that is completely removed by this correction effect in this scene. Similarly, the stripe at 4.5 kilometer scale and 2.25 kilometer scale, those are removed, but there are still large noise peaks that are to the right-hand side of that spectrum. There are three big ones. One is at 8 pixel periodicity, one is at 4 pixel periodicity, and the other is at 2.3 pixel periodicity. So the next challenge is to get rid of those spikes. In the cross-track direction, it's much more of a mess and hard to figure out exactly what's going on.
1 minute left.
So how well does all of this work? The left-hand image is the raw image at the 10.49 micron after the focal plane correction. I've done a Sobel gradient on that, and you can see that noise overwhelms the Sobel gradient. There's a hint of the very sharp gradient that's in the upper left-hand corner of the original image. There's a hint of that in the Sobel gradient, but you really can't detect much else. This is all done before resampling. Then once we do our Fourier notch filter and a wavelet filter, we do the Sobel gradient again, and now you can start to see a lot more detail of the gradients, but there's still a huge amount of noise that is a big problem. once we try some other kinds of gradient filters, the Pavel Holoborodko filters that Daniele Ciani found a few years ago, those are quite effective at removing a bunch of this smaller scale noise. So we now, on the right-hand image, the combination of our notch and wavelet filters, we end up with a much better ability to detect gradients. But it's still not at the stage that we can do with many of the operational sensors because this is just much more noisy. In the lower graph shows the spectra from these various approaches, and you can see that we've been able to get rid of those three big peaks on the right-hand side of the spectrum, but there's still a lot of remaining noise. So that's where we are. We've had a relatively good success at the removal of general biases. We've been able to get rid of a bunch of the focal plane noise. The denoising of the remaining noise is still not completely effective. Resampling, we can get an even bigger improvement because we get rid of the focal plane bias at the one end of the focal plane by dropping one end. So I'll stop there.
Thank you, David. We're gonna take a question later. Let's move on to the next speaker, Daniel. L4SST intercomparison within the Copernicus Climate Change Service Evaluation and Quality Control. So if you're ready, please go ahead.
Okay, hello everybody. So on behalf of the long list of authors you see here, and together with Antonio, later on we are going to present some work we have been doing in a framework of the Copernicus Climate Change Service, and in particular for the evaluation and quality control of climate data records in the Climate Data Store. So I will start just briefly introducing the Climate Change Service implemented by the European Center Medium Range Weather Forecast on behalf of the European Commission. The aim is to inform on past, present, and future climate. And key services are summarized here, from information which is provided to a broad audience to examples of data usage from industry and stakeholders. We focus on the Climate Data Store, which is known by the majority of the attendants. So that provides access to climate data records from satellite, in situ, climate projections, modeling for land, ocean, and atmosphere domain. So we focused on key questions that might be useful for users and also non-expert users on which data set is best fit for their own application. And the evaluation and quality control framework is based on three main pillars: quality assurance, assessment, and fitness for purpose. So the first is a check of the documentation that comes along with the data available in the Climate Data Store. A quality assessment is an implementation of scientific assessment, also in perspective of guiding non-expert users, which is available via Jupyter Notebooks and accessible freely through the Climate Data Store. And the fitness for purpose in the end is a text-based assessment that summarizes main features, key strengths, and limitation of the dataset. We focused on satellite SST, and this is the current suite of products available through the Climate Data Store. The sea surface temperature and ice surface temperature, which is still currently under evaluation. So we mostly focused on the ESA CCI version 3 and 2.1, and also the GRIS multi-product ensemble. And all the, let's say, all the EQC procedure has been run on a platform that enabled fully traceable passages through the evaluators and the ECMWF officers. Any information on the quality assessment is available through the Quality tab in the Climate Data Store webpage, which is accessible through the QR code you see here. So just to provide a very brief overview of what we have been doing regarding quality assurance, we had to check a series of requirements which were set by the ECMWF. And you have an example of what you can find on the website on the Climate Data Store for quality assurance of GIMP and CCI. Whenever you see a green tick, it means that the evaluators consider that all the requirements were fulfilled. Anytime you see a warning, it seems that some inconsistencies have been checked. For instance, we found that in version 2.1 of ESA CCI, no monthly averages were available as requested by C3S, which has been updated now with the version 3. And the main issues with GIMP, at least on the climate data store, is the unavailability of planned evolution for this dataset, which is currently available until 2016. Regarding fitness for purpose, we just highlighted main strengths and weaknesses and also provided additional recommendation for users. This is based on literature, but also take-home messages from the different quality assessment. So for instance, GIMP is particularly useful for its accuracy, higher than any of the contributing SST analysis, and availability under CIs is being considered as a limitation, and it's very useful for intercomparison studies. For CCI, the independence from in-situ data is a plus, as it facilitates assessment, and it's been used for several applications, from marine waste monitoring to ecology and ocean dynamics. And one issue is the anomalies found in the earlier stages of the time series. Regarding quality assessment, we give an overview of what we have been doing. Just a few key examples. We provided an assessment of mean variability and mean status. So in the 82-2016 period, we found that GIMP, particularly in the tropical Atlantic and Indian Ocean, was highlighting a large positive bias compared to CCI version 2.1. We also provide an intercomparison of sea surface temperature trends from GIMP and CCI version 2.1. And you might see that even regarding the trends, you have a very strong signal in the tropical Atlantic and Northern Indian Ocean, much larger compared to GIMP. And also monthly averages time series highlight that at the beginning of the time series, CCI is slightly underestimating SST. But this is reported in the literature as a known issues, and that generated these anomalous positive trends. And GIMP was very useful to detect these inconsistencies. In the latest release of CCI, this is fixed, and you can see a reduction of the very strong signal in that area. We also provide an assessment of feature resolution. This has been quickly presented on Monday as a task team ICTT activity. So this has been done through spectral analysis, and we are here reporting. Thanks. We are here reporting an example in the Kuroshio currents, and you see the spectra of CCI in blue and GIMP in red, intercompare with the predictions from geostrophic turbulence. And so this was a quite expected result, as we all, so many in this community know the procedure behind the construction of GIMP, but it is useful to guide users to understand which dataset best fit applications related to mesoscale characterization. So considering the Rossby radius of deformation in the area is around 40 kilometers, you can see that both datasets are good for large mesoscale characterization, while CCI best fits the smaller scales of smaller mesoscale region. So based on this experience, especially the last assessment, we are now developing additional metrics which might be applied even beyond studies within the C3S EQC activities. And I leave the floor to Antonio, who will briefly present recent updates. Thank you.
Thank you, Daniele. Well, thank you, Daniele. Well, staying in the framework of the intercomparison of level 4 SST products, we've been investigating effective spatial and temporal resolution by adopting a spectral analysis approach. The data we analyzed are OSCE level 4 and is a CCI version 3, together with the global tropical Moore buoys array Pirata and Rama buoys for the temporal diagnostics. Starting from the spatial one, we divided each daily SST field into zonal sequences within fixed size boxes. Then for each sequence, we've been computing a multi-taper power spectrum and compare it with an AR1 red noise background. Then finally, we compute the spatial resolution limit as the smallest horizontal scale with spectral power still exceed the 95% significant threshold. And yeah, we can interpret this also as the smallest feature size that is still distinguishable from the noise background. Moving to the temporal diagnostics, we rely on Ballarotta's work, and we compared buoyant satellite spectra, and the effective temporal resolution is computed as the shortest period where the unexplained satellite variance is still less than 50% of the buoy variance. I reported in the next slide a couple of examples. Starting from the spatial one, we can see and notice a clear distinction between a region with high spectral intensity and the small scale range. Whether in the temporal one, we assess down to which time scale the satellite still captures the buoy variability. Moving to the global results, as we can see from the first plot, the effective spatial resolution, this is a mean, and it's not uniform. We utilize regions with high spectral intensity at finer scales, and these regions align with dynamically active areas, as we since this kind of diagnostic should highlight this kind of regions. And in the lower left plot, we can see the differences between CCI version 3 and Ostia. And CCI version 3 in spatial resolution shows coarser scales with respect almost everywhere with respect to Ostia. And moving to the temporal one, we analyzed Ostia and the mean effective temporal resolution, which is derived from 1 year global tropical moon buoys array matchups, is ranging from 3 to 20 days with some outliers. Concluding, this kind of analysis fits within the C3S ECQ framework, and which aims to provide intercomparison assessment for SST level 4 climate data record. And our analysis also aims to provide a quantitative framework to intercompare level 4 products, and also for assessing how some mesoscale features are represented in the analyzed products. So starting from this one, we hope to extend the analysis to additional products. Thank you very much.
Thank you, Daniel. And okay, we're gonna take a question later. Next, we move on the third speaker, Dr. Aro, the single sensor error statistics for INSAT 3DS SSD. If you're ready, please go ahead.
Good morning, everyone. Good morning, everyone. I'm Neeraj Agarwal from Space Application Center, and this is basically single sensors error statistics for INSAT 3DS SST, and we are going to show the bias characterization over the Indian Ocean. So this is a very preliminary study, and the origin started actually last year GHRSST meeting at Copenhagen, where I had some discussions with Pallavi from Bureau of Meteorology, where actually this particular term SSES was quite new to us, and we had problems, in understanding this and getting enough literature on this. So Pallavi extended her help, quite grateful to them, the team, and then we started working in a collaborative manner. So this is an ongoing study, still not completed, so I'll be showing some of the preliminary results. So this is the outline. So why SSES are required? So this is basically to make the data GHRSST compliant in order to improve the level 4 global analysis, and also make it easier for the people who are doing data assimilation of different data sets of sea surface temperature from different sensors. So it is better to quantify the uncertainties of each of the sensors so that it makes their life easier when they are assimilating the data in the models. And also, it helps in correcting the retrieval errors. Know that the satellite sensors are affected by various varying conditions like the viewing angle, the geographic location, and the environmental factors such as the diurnal warming or cloud cover. So SSES models these effects to provide a more realistic error estimates than a single one-size-fits-all number. So I showed this particular slide in my agency report presentation. So this particular satellite INSAT 3DS is better than its previous generations, 3DR and 3D, in terms of the better black body calibration. And so this is the overall statistics on the right-hand side, the scatter from the matchups created during 2025 to April 2026. So it has a negative, overall negative bias of 0.5K approximately. And on the monthly scale, if you see the time series of the root mean square errors and the standard deviation from June 2024, you can, so this is shown here. And the red line indicates the period when the G6 corrections were applied. So you don't see much of an effect, but yeah, this is in an average sense, but definitely it had some regional implications. So these data sets are available at mosdec.gov.in, and our data products team is in process of releasing the data prior to September 2025. So in this analysis, we have basically used this retrieval equation for the sea surface temperature retrieval. So this is the nonlinear SST algorithm, the standard equation, and these are the coefficients. And this is the cloud mask algorithm, which is applied on the data set. So again, this some of the part was taken from the ATPT of Savory by making use of the two brightness temperatures, TIR1, TIR2, and also the visible and the SWIR channel albedos. And so this is this is the category of the cloud mask that we applied. So basically the 5 categories: the clear, probably clear, uncertain, probably cloudy, and cloudy. And so we took the data, IQM sea surface temperature data from June 2024 to April 2026, and the matchup criteria was the nearest pixel SST from INSAT within plus minus 3 hours. And from June 24 to April 2026, on what you see on the left side figure is the distribution of the matchup data points. Around 6.65 million matchup data points were there. And if we categorize them into before G6 and after G6 corrections, so you can see that the distribution is quite similar. And after G6, we had left with 1.3 million data points. And if we look at the monthly distribution of the matchup data points, you can see that from September 25 till April 26 onwards, the distribution is uniform, but there is a definite bias in the distribution, in the sense that the southern Indian Ocean is densely covered with the in-situ data measurements, whereas the Arabian Sea and the Bay of Bengal and the equatorial Indian Ocean is data void region, I can say. So this is one concern. And coming on to the differences between the INSAT and the IQM data, on the left-hand side, you see the histogram of the differences from September 25 to April 26. So most of the values are having a difference of around negative 0.5 K. However, there are many values which are also coming in the range of -1 K. On the right-hand side, and these red lines indicate the 90 percentile of the values. And on the right-hand side, you can see the distribution of the scatter of the differences versus the time. So you can see that the distribution is fairly even. I mean, it is not changing much with time. Of course, the data density has a little bit changed, but as far as the range is concerned, it remains in the same range. And these are some of the scatter plots which are showing, basically these are those parameters which will be used further in the bias model. So shows the variation of the INSAT and IQAM SST differences with various parameters. First one on the top left corner is the range of the SST itself. So you can see that there is a slope. So more values or the more larger differences in the higher SST ranges. And of course, the data density is also there more because those are the typical tropical SST values. And then you see with the difference of the INSAT and IQAM SST with the variation with the longitude. So the Western Indian Ocean is densely populated with the in situ measurements. That's why you see more observations over there. And there is a slight upward slope in the scatter. Of course, on the eastern part of the equatorial ocean, again, the data density is quite less, and the values are going up to between -2 to +1 degree. Most of the values are like, and there are many outliers also. The third one is the variation of the INSAT and IQAM difference, SST difference with the latitude. So you can see that there is a negative slope downwards, and however, there are hardly few values if you go in the northern Indian Ocean, especially north of 10 degrees south, the Indian Ocean region. And these are the variations shown with the satellite zenith angle, basically showing the field of view of the satellite, how the variation of the differences are there. So again, there are certain, there are slight slopes, slight correlation is there, and also with the diurnal changes. And the last, it is showing the scatter between the SST and the latitude, and the color indicates the difference. So you can see that the maximum difference lies in the range of the cool bias, which is around 295 to 305 Kelvin. So these are some of those parameters which were used in the bias model. And further to this, it was suggested that we can also remove some of the outliers by considering certain more quality flags. So one of the quality flags could be that we applied was basically the cloud edge masking, because there could be the cloud leakage. And so what we did is that any pixel within 2 pixels away from the cloudy pixel, we masked. So finally, we assigned 2 quality flags. A pixel is assigned a quality flag of 5 if it is the clear sky probability is greater than 90%, and the nearest cloudy pixel is greater than 2 pixels away. Else the pixel is assigned a quality flag 0. So what you saw on the top 2 figures was the previous one when we apply a simple cloud mask, and the bottom one when we apply these additional quality flags. So we have a category of 0 and 5. So 0 we are not using, only the values with a quality flag of 5 shown in the left panel are being used. And in the IQAM datasets also we have avoided using the research vessels and the ship-based observations. So this is the final distribution of the matchup data points. So you can see that a lot more points have gone from the western equatorial Indian Ocean. So coming on the bias model, so this bias model is the Bureau's bias model, which they have applied on the Himawari 9, and it has been used as it is on this INSAT matchup points. So it has a additive bias and a multiplicative standard deviation. So so they are dependent on the field of view, the diurnal changes, and the geographical location. So we apply a rolling 90-day window, which is adjusted every day. And so as I told, 7 parameters have been included. And elasto-lasso regression is applied to the highly correlated component. So this model is as it is used in Himawari and applied on INSAT. So this is the performance of the model. Basically, this graph shows the correlation between the satellite and in situ SST difference with the bias of the bias estimate which we have done. And these 3 colors indicate the 3 components. And what we can see is the bulk variation is geospatially distributed, and the maximum contribution comes from the geographic location. And the declining correlation over time, we need to investigate that, why it is happening. So whether it works, yes, the bias model as it is, it works for this particular matchup data set. And so what we show here, the blue is the original difference between the INSAT and the ICOM data sets. And once you applied the bias correction from the model, so you get, basically you can see that the bias comes around to 0. Of course, we have not applied it to the full disk. We need to see that. And a lot of work is still remaining. So to summarize, we see that the INSAT 3DS, the maximum values are having a 0.5 K cool bias. And the Himawari-based empirical bias framework can be applied to the INSAT matchup data and gives a meaningful reduction in the average satellite minus in situ difference. And the current results suggest that the correlation is useful, but the interdependent behavior and full disk implementation still need further study. So the way forward, so we want to extend this bias correction methodology to the full disk and refine the bias model, fine-tune the bias model for the pre-G6 period as well, or we wait for the G6 corrections, and then investigate the time evolution of bias more carefully to understand the apparent change in performance over the sampling period, and validate the corrected product against an independent set of ICOM observations. Thank you.
Thank you. Next speaker is Christopher, assessing the uncertainty information in GHRSST gap field product. Please go ahead.
As we know, level 4 products, gap-filled products from GHRSST, tend to be the most popular with users because they're so convenient to use. Now, in those products, we have an analyzed SST, which is provided, and also an uncertainty. It's called analysis error presently. And although the use of the uncertainty information has been perhaps less fast to be taken up by users, I have noticed that uncertainties are being used by more users in recent times, which raises a question. How reasonable are those uncertainty estimates? We have to be careful when we talk about the uncertainty of a product, because there can be 2 things. There can be the uncertainty that is in the product, which we might call the producer estimated uncertainty, or we might say it's attributed uncertainty. I'm going to use the term prognostic uncertainty, the uncertainty you attribute to the data. But are those attributed or prognostic uncertainties realistic? Well, the way you can assess that is by assessing the uncertainty by some other means. And that gives us a diagnostic uncertainty. And ideally, the prognostic and the diagnostic uncertainties should agree. And this talk is about whether, in fact, they do or do not. So just to say that again in one way, there are 3 ways of estimating the uncertainty in a product. There's what we do as data producers, which is probably either a propagation technique or something that's a statistical estimate of uncertainty. If you have a reference data set, which is independent of your data, you can look at the uncertainties by looking at the comparisons, but you need to know the uncertainty in the reference as well as the uncertainty in your data if you're going to do that. And the third thing you can do is look at variability of differences between different representations of the same SST. And those are collocation methods. So in this talk, I'm addressing 4 GRIST data sets. There's CCI, there's the MUIR, that's the 0.25 degree version, the daily OI, which is also in the same resolution, and the microwave optimal interpolation, microwave only. The SST CCI has been regridded to 0.25 degrees using the surftemp.net website. So that's our website, and that propagates our full resolution uncertainties to this resolution using a simple method. Now, these 4 are chosen because they have some level of independence between the 4. So CCI and microwave OI, neither of those ingest in situ data. Microwave OI, it's the microwave only version, so that's independent of the infrareds. The analysis systems are very different between MUIR and the others, and also DOI and the others. They have quite different ways of bias correction in DOI, for example. So there's some degree of independence between these data sets. Ideally, I would like to compare all of them against a high quality reference, and the best reference would have been Argo. And there is a GRIST recommendation, long-standing, that level 4 analyses do not data because the most useful way of using Argo data for us is as an independent reference. It doesn't really add much to the quality in L4. Unfortunately, I believe both MUIR and DOI ingest Argo, so that's not available to us. Instead, to go for an independent reference, I've had to go to radiometers. And very grateful to Fred Wimmer for helping me get a radiometer-based data set. There are a number of ISRs and Marys and a sister radiometer that I've used here. Quite a lot of daily files for these different ISR and other radiometer models. And in the Ships for SST project, there's been a lot of work done on estimating the uncertainties of those reference data. So it's a good reference data set. From that point of view, the uncertainties are well understood. The limitation of using radiometers is the geographical distribution, which is extremely uneven and focused very much at the Atlantic between about 40 and 60 degrees north. So the results we can get from a radiometer comparison are very much tied to that geographical distribution. So to use a reference to assess a prognostic uncertainty, or to validate your prognostic uncertainty, you take the difference between the analysis and your radiometer. I've debiased that here. And once you've done that, you're left with what should be a normal distribution. And for any given point, that normal distribution would be the sum of the square root of the sum of 3 terms coming from the analysis uncertainty, the uncertainty of the radiometer observation, and some representativity difference, because the radiometer does a track across our cell, whereas the level 4 is representing the whole cell. Now, we don't know what that representativity number is, but we do know its plausible range from our experience in doing normal validation, somewhere between 0 and 0.2 Kelvin, probably significantly less than 0.2. If we rearrange that and we take the ratio at the bottom, what we're left with should be a Gaussian distribution of 0 mean and unit standard deviation. So let's look at the distributions that actually apply, assuming 0 representativity uncertainty. And we can see that we have quite nice comparisons between the theoretical Gaussian curve in the line and the actual distributions for CCI and MUIR. Not bad for the REM data, and then the DOI disagrees quite a lot. It's the actual distribution of differences is a lot wider than you'd expect from the DOI uncertainties. So that's assuming 0 representativity, and apart from REM, the the locations of these histograms are all identical. You don't have the coastlines around the REM dataset, so there's a slightly different distribution in that one. If then we look at the standard deviations of these distributions and then use our formula for different values of the representativity uncertainty, given that we don't know it, we can see whether this story holds up irrespective of the representativity uncertainty. And there are three different ways of calculating the standard deviation on the graph in different types of line, and the three colors are the same as the color scheme for the previous slide. And you can see that the message doesn't really depend greatly on what that representativity uncertainty is. We still have the three of the analyses around about 1, which is the ideal number at the bottom, and then the DOI sticking out a bit. So DOI looks quite different in its uncertainty compared to the others. So that was method 1, and now we're going to look at collocation methods for assessing the differences and the discrepancies in uncertainty. So what we're doing here, most well known, is the triple collocation method. If you have 3 observations of the same quantity and you take the differences pairwise, that gives you 3 equations that look a bit like this. The variance of the difference between any 2 is just the uncertainties in the 2 adjusted by any correlation in the error that exists between those 2. Now, if the error correlations are 0, you've then got 3 equations and 3 unknowns, because the 3 unknowns are the uncertainty terms. So if we make the assumption that the error correlations are 0, you can solve this and extract the uncertainties. So that's the classic triple collocation approach. Of course, the caveats are that if there actually are some definitional uncertainties between your different representations, that goes somewhere and you don't really know where it's gone. And there is always, at some level, a lack of independence between GRIST datasets. So a collocation method, you've got to be a little bit cautious. But as I explained, the 4 I've chosen are independent in different ways. You have either US or European sensors, different analysis methods, or different wavelengths of observation going in. So that's triple collocation, probably familiar to many of you. With 4 data sets, you can also do a quadruple collocation technique where you're looking at the differences between all 6 pairs of differences. From that, you can estimate the uncertainties in all 4 plus 1 correlation. So that's quite useful because then it's giving us a sense of how much correlation there really is between the errors in these differences. So what I did was to do all the possible combinations. So with 4 data sets, there are 4 different ways you can do triple collocation, and you can make the correlated estimate one of the 6 combinations of pairs. So that's what's the permutation that's explained on the left. And the important thing here is that when you look down the columns of numbers that happen, they're not jumping around very much. So whatever degree of correlation there is, it's not completely destroying the information that we're extracting by these collocation methods. It's quite robust. And from now on, I'm just going to use what's shown in the bold at the bottom, the average of the columns, essentially, wherever. Also estimated, and that's in the left-hand column, and you can see that they're all fairly low, which makes the collocation methods possible. So this is the diagnosis of these data sets on a global scale over a more than 20-year period. And you can see that the CCI, MUIR, and REM analysis all have uncertainties which are quite common, and DOIs is coming out a bit larger. How do they compare to what is in the product? So this is what we're trying to get to, and now we're going to see the answer. Well, the CCI uncertainty is pretty much spot on. The REM one, pretty good as well. But the MUIR uncertainty is way better than they claim. So they're under claiming in terms of the accuracy of their product. And the DOI uncertainty is way higher than they claim. So they're greatly overclaiming compared to the actual accuracy of their product. And so this means that we do have this issue that the uncertainty that's in the data set, we've got to start questioning that now that users are beginning to use them to make sure that they also are realistic as well as the SSTs. Now, with enormous data sets like this, we can go a lot further, of course, and start decomposing this into different times and places. So if we do this latitudinally, this again is the diagnostic uncertainty for these data sets across the full time series, but at different latitudes. And you can see that there's a lot of interesting information in a plot like this. Clearly, CCI is doing extremely well in the tropical parts of the ocean in terms of its uncertainty, dipping down to almost 0.1, which is probably to do with the fact it's slightly delayed mode compared to the others. So we can use our CCI, we can ingest our CCI with level 3 observations, which have been homogenized very carefully. But I think our analysis system is letting us down once we get into the high latitudes and we've got lots of cloud and quite a lot of variability. So the CCI in 45 degrees north is coming out less good than Muir and the microwave one. So we can decompose this by zonal amounts. We can also look at how the uncertainty varies over time. And this is quite instructive. We see that the high uncertainties in DOI have been improving over time. They were very high, just going back to the early part of the record, but there's been a couple of changes to the method over time. And in the recent years, DOI is in the pack with all the others in terms of its uncertainty. I mean, this is an argument really for reprocessing DOI, possibly, because we saw from Ruben's talk that instability in the uncertainty is something that can influence results when you're looking at climate as well as the actual SSTs. And there's a lot of other information about that in there about where different products are, different time periods have different levels of uncertainty over time. So we can go another stage further with these collocation methods and really try to break it down geographically. So again, these are diagnostic uncertainties as maps across the world. And you can see the sorts of patterns you'd expect. In the highly variable regions, the uncertainties are larger because we're not fully sampling all that variability. And so when we do a level 4, of course, the uncertainties are higher. You can see that quite clearly on CCI. I think the analysis method for Muir is dealing with highly variable regions somewhat better than the CCI analysis method. So it's less the uncertainty is less high over the Gulf Stream, for example. With microwaves, you're less prone to that, or you should be, because you're seeing through the clouds, so you don't have quite that same sampling restriction where it's very cloudy in the higher latitudes, and you see that reflected in this diagnostic uncertainty as well. And then we see the pattern in DOI is very similar to the other infrared-dominated. The pattern is very similar to the other infrared-dominated L4s, but is a higher value overall. The one thing that struck me as not what I expected was the warm pool. Infrared, that's the most difficult place to derive an infrared SST, and yet we don't see any uptick and uncertainty in that region. Probably because the SSTs are quite stable, and we get to see them sometimes, I suppose. But I was actually very surprised that there wasn't a peak around the warm pool as well. So again, these are the diagnostic uncertainties from collocation. How do they compare as patterns with what's in the data? So in this plot, we've got the empirical diagnostic uncertainties in the top row and what's in the product in the lower row. You can see that in CCI, the pattern of uncertainty that's being attributed to the data really matches very closely the diagnostic pattern in the lower row. The same is somewhat true of REM. There's not as much, the attributed uncertainty doesn't reflect the dynamics as much as it needs to in the case of the REM analysis, but the latitudinal variation is mostly good apart from near the sea ice areas. And then looking at the Muir case, the Muir has a pattern of uncertainty that's very similar to the other infrared-dominated ones, but is very bland in what's attributed. It looks in the plot like there's no variation at all. There is actually a spatial variation in the uncertainty in Muir, but it's much suppressed compared to what it should be. And then in DOI, it's sort of got some idea where the uncertainty is good or bad, but is quite smeared out compared to the actual pattern. So actually, you'd be better off using the uncertainty from CCI for the Muir than you would be using Muir's attributed uncertainties as it currently stands. So I think the conclusion from that is that it is necessary to question the prognostic or the in-product uncertainty values. And I've done that using those two methods, reference SST comparison, which needs non-ingested data. So that's limited just now to radiometers. The collocated discrepancies seems to be very successful. Error correlation is a concern, but I've tried to handle that by doing every possible combination, and it doesn't seem to be too much of a concern for these quite independent data sets. Because Argo is ingested in some of the L4s, we can't do a really good globally distributed reference SST comparison, and I believe that to be quite unfortunate. So maybe that's something we should return to. We don't have an ideal community reference for this sort of work as it currently stands. The collocation methods look particularly helpful when breaking uncertainties down into space and time zones, and it's really reassuring to see those diagnostic uncertainties emerge in the patterns that we would have expected from the physics. And in terms of what is in the products, the prognostic uncertainty in some of the products is highly plausible, and in other of the products it's highly implausible, with both significant underestimation and significant overestimation in different L4s as it currently stands. And that obviously means that we are potentially greatly misleading the users in terms of the uncertainty. So this is something that we do need to sort out. And I believe that user interest in uncertainty is, in general, at last increasing, given the effort we've put into creating it over the years. I'm finding more people are looking at the uncertainties and using them. And that's also going to be given a boost with the move to GDS3. So this is something we need to look at, I believe. Thank you very much.
Thank you, Christopher. Okay, now we have time for questions. Is there any question or comment? Please.
Okay, thank you, Chris. Indeed, I found it very interesting because we kind of deal with that. I don't know if you are aware. In our team, a few years ago, we developed a correlated triple correlation, and I think you might have come to with a similar equation or something like that. And we tried in the framework of an ESA project to make an evaluation of comparing different L4, but then you just find it that they are not that independent. So we tried. I can show you the results. So they are kind of similar. We found we can discuss later. So I think that we should, as a community, we should just follow on this and this is an intercomparison level 4 task team activity, so that I would be willing to continue and discuss with you if you find it right. So that's it.
You have a comment? No?
That's great. I'm pleased that, although we've already given you some more work for this task team, that you're keen on this activity.
All right, next, please.
Chris, thanks for the excellent talk. Yeah, we can surely discuss later. A quick comment is that also we can take the opportunity within the GRIS community to define reference methods for the attribution of the SST analysis error field in order that possibly we could use a common methodology, if possible, among the huge variety of SST products. That's my comment. Thanks.
Yes, thank you. I think it would become harder with some comparisons because some of the level 4s are less independent than the 4 I've chosen here. So I'm not sure whether this co-location method is a universal one. We maybe have to try it and see what the correlation is doing to the answers. It's maybe something that we can return to a bit like the CDR activity, the CDR assessment activity, which GHRSST has had nominally going on for a number of years, and it could be an extension to that. So maybe it's time to look at that activity again. You want to comment on that, John?
Sure. It is going, but going slowly, but we can, once it's got where it needs to, we can start thinking about adding to it. But probably again, slowly. Yes, with the level 4 team, yeah.
I mean, the co-location methods are also able to be used with level 3, although I didn't show that in this talk, but you can do it with level 3 data as well, just to note that. I had a question for you, David, actually, if I may. Is that okay? David, in your work on the EcoStress focal plane errors, were the focal plane artifacts similar between the two thermal channels, or were they more or less independent between the two thermal channels? And if they're independent, can that be used to help remove some of them?
They appear to be largely independent. So it's because there are actually physically different parts of the electronics that are involved in the detectors. It's a butcher block detector system. So there is a I think it's a 256 by 256 array of detectors, and they have stripes that for each of the channels. There's a filter stripe for each channel, and so they're in physically different places on the circuit board, and there just are differences in behavior. And some of what's going on is that there are differences in the amount of time delay integration going on. They made some decisions to use 4-pixel time delay integration for some channels and 3-pixel for others. So the reason the 12.09 micron channel is so much noisier than the 10.49 is because it's a 3-pixel TDI rather than 4-pixel TDI. And so there are things like that going on, but the non-uniformities, because they're in different places in the focal plane, each channel, they're not fully correlated. There are crosstalk problems too, but it's very hard to figure out exactly what's going on because we don't have a timing diagram for what's for anything.
Okay, next, please.
Okay, I agree with you that the community will, in the next step, try to use this information uncertainty. So it's crucial that we found a way to identify the uncertainty. We know exactly that the uncertainty we put in the level 4 product is something related to the statistical interpolation method and comes from an hypothesis of the accuracy of the input data set. And obviously, this is, I was also curious from your plots related to the difference of the uncertainty at latitudinal level. And so if I look, I correctly show the plot, it seems to me that the CCI increased a lot the uncertainty after at the middle latitude towards the and this not happens to the mirror data set because probably because are microwave, and so they have information at higher latitude, I think. So perhaps the combination of a future combination of using microwave and infrared can help us to improve this situation.
Yeah, yes, it is noticeable that REM microwave only and Mura, which ingests microwave, do not have the same level of change. But I do wonder whether it's as much to do with the mode of gap filling that CCI is employing compared to the observations, because Mura is quite infrared dominated, more or less. So I think that's something to be try to untangle that.
I have a comment on this issue. As a physical oceanographer, because the polar region or subpolar region, basically we call the beta ocean. The beta is saline contraction coefficient. So the SST usually tend to underestimate the small scale features. So that's why I'm using radar altimeter data set for understanding the ocean circulation. So, so maybe that is why the polar region, the error is getting higher, I think. Anything else?
So Chris, the uncertainties that we saw from REMS, why do you have one question is, do you have any idea why they blew up so much in the Southern Ocean and it didn't really seem to be reflected in reality? Any idea at all? Because it was just a huge jump.
Yes, I should have excluded a bit harsher. So the global values were based on 70 to 70, and really I should have cut off at 60 in the Southern Ocean. So that's one thing I'll redo before publishing this, because I believe that that's just guessing what the temperature is where you've got ice in a slightly different way to the others.
Oh, right, okay.
And of course, actually it's worth saying that the apparent decrease near the poles of uncertainty in this plot with the latitude is an artifact of the fact that all of them are guessing what the temperature is under the ice. At this point, it's not really that low. They all have a correlated error there.
Yes. The other thing is that the Mura was coming out at slightly better than everything else, 0.24, which we do, I mean, I know it does ingest Argo, but I've not seen those actual validation numbers on other from Mura from something like Argo. So are you happy with that number? Do you think that it is? Because, I mean, obviously it's not the ultra high resolution. Is there something really special about the fact that Mura is processing at the very high resolution and then doing something smart to get down to 0.25? Or, so that's one thing. And the other thing is I've not seen Mura validate that well. Is it the 0.25, smoothing to 0.25 that makes it less noisy, or what's going on?
I guess you wouldn't get the same answer if you used the 1 kilometer Mura by a long way, because of the extra noise levels you'd have at 1 kilometer, yes. But I haven't done that, so I can't put my hand on
Okay.
Hartman.
And just, I said, just running the 0.25 against Argo. I know it's got it in it, but did you get those same numbers? Well, I mean, I know you don't want to use Argo for Mura because they ingest it, but
yeah, I
said the Argo values that I've seen for the 1 kilometer is a lot higher than that. So
yeah, well, yeah, you just don't know what you get if you validate against something that's been ingested. You should get an artificially good result, but you don't know by how much.
All right, we have 10 minutes only, so okay. We would like to move on the next speaker. Sorry about that. Okay, the next speaker is Swapna.
Yes, I am available.
Online, okay.
Yes.
Okay, the scheme-box SSD harmonization and uncertainty assessment for INSAT geostationary observations over the North Indian Ocean. Can you show the PowerPoint?
Yeah, shall I share my PowerPoint?
Yeah, please share. We can see your slide.
Are you able to see my presentation now? Hello?
It's coming, not yet.
Shall I start my presentation?
Not yet, please wait. We will
Okay.
tell you. Now, we are good to go.
Yeah. Very good morning to everyone. I'm Dr. Swapna from National Remote Sensing Center, Hyderabad, ISRO. Today I will be presenting on our work, skin bulk SST harmonization and uncertainty quantification for INSAT 3DS over the North Indian Ocean. These are my co-author, Dr. Rajesh, Dr. Nagamani, Dr. Aparna, and Dr. Prakash Chauhan. As we all know that sea surface temperature is a key essential climate variable governing air-sea interactions, energy, momentum fluxes, gases, and gas exchanges between ocean and atmosphere. So, however, the satellite infrared radiometers measures the ocean skin temperature, whereas in situ buoy observation represents the bulk SST. The differences arises due to this cool skin and diurnal warm layer processes. So, accurate conversion of skin SST to bulk SST is therefore important for climate quality SST products and many oceanographic applications. So, the recently launched INSAT 3DS provide high frequency sea surface temperature observations over the North Indian Ocean, offering an opportunity to investigate regional skin effects and their variability. As I said before, the ocean skin effects arises due to the cool heat losses from the ocean, like long wave radiation flux, latent heat flux, and sensible heat flux, whereas the warm layer effects occur during daytime under strong solar heating and low wind conditions, leading to warming of the near surface layer. So several parameterization schemes have proposed in literatures based on these parameters. So our objective is to characterize the skin and bulk SST differences over the North Indian Ocean and investigate their dependence on these wind speed, net heat flux, and local solar type, and also compare with the existing correction schemes available in the literatures for the INSAT 3DS SST observation. So for the data, the skin SST observations comes from the INSAT 3D SST. For bulk SST observation, we have considered the Omni buoy network, ocean moored buoy network for North Indian Ocean from INCOIS we have obtained, and the wind speed and fluxes are obtained from ECMWF data, and we have analyzed this data from 17th May 2024 to December 2025. So for the collocation, we have used a spatial window of plus or minus 4 kilometer and a temporal collocation of plus or minus 1 hour, and a physical SST range of 20 to 35 degrees centigrade is applied, and we have kept the satellite, that is skin minus bulk SST difference should be within the 3 degrees centigrade limit, and a temporal consistency check with the 5-hour rolling window with 3 sigma spike detection is applied. So after this collocation, we have carried out the characterization of skin and bulk SST difference using INSAT 3D and buoy SST, and developed the parameterizations of skin effects based on wind speed, local solar time, and net heat flux, and again the corrections applied after these parameterizations. This comes the results section. As I told, after quality control, we have obtained 41,840 collocated matchups. The histograms on the left side shows the distribution of delta T observed, defined as the INSAT SST minus buoy SST. It is negatively skewed with a mean of minus 0.67 degrees Celsius and a standard deviation of 0.56 degrees. So this confirms the persistent cool skin bias in INSAT 3DS observations. Around 90% of data is underestimated in comparison with GHRSST, and 4% is overestimated and 5% is neutral. So around 74% of data is showing within -1 to +1 temperature difference range. So coming to the right side of plot, this is before correction, how the inside 3DS is correlating with the inside GHRSST we have carried out. So this scatter plot shows that a correlation of 0.896, RMSE of 0.88, and a bias of -0.67 degrees centigrade. So here we have, as previously we observed the delta T observed, that is INSAT minus GHRSST. Each driver like wind speed, net heat flux, and how local time is affecting, we have independently observed the wind speed effect on this delta T observed. We have found a linear fitted relation that is consistent, physically consistent with reduced cool skin effect at higher winds due to enhancing mixing. And this B panel shows the dependence on net heat flux of delta T observed. It is also linearly fitted with the relatively moderate relationship with our data set. And panel C shows the diurnal cycle of delta T observed with local time. And here we see a clear sinusoidal signal. This captures this transition from cool skin dominance at night to warm layer development during the daytime. So here D panel shows our key findings, where this we can compare these three correction. Wind correction, we named it as delta C1. Net heat flux we named as delta T C2, and time correction delta T C3. So when we plotted these corrections with respect to the local solar time, if you see the delta, the diurnal correction seam is almost nearly close to the zero line. This is the zero line, whereas delta C1 and delta C2 are the wind speed and net heat flux corrections. They are moderately reducing the differences, but whereas delta C3 is on all times, it is very close to the zero line. So based on this, our findings, we have applied the corrections to our INSAT 3DS. So here, after the correcting the INSAT 3DS skin SST, we converted into bulk SST and compared against with the GHRSST observation. The RMSE has increased 0.9, correlation has increased to 0.9, and RMSE is reduced to 0.56, and bias is near 0. So here the not only the our parameterized correction, we have also compared with the existing models like Donlan et al. 2002, Minnet 2011, and Alapatu 2017, and Feral 1996. So it coming to the Donlan, it underestimate the bulk sin SST for our region with a bias of -0.91 and RMSA of 1.7. Coming to the Minnet model, it is also in similar kind, like bias of -0.96 and 1.13. And Alapatu is a 3-step correction scheme where it involves wind speed, time, and long wave radiation. So it is giving a relatively less RMSA of 0.82 but a bias of 0.38. And Feral et al. Is a physics-based model, but still it is also giving RMSA of 0.85, and a bias of negative bias is observed with 0.53. And the first 1 to 3 models are wind speed and long wave radiation time dependent empirical schemes, whereas Feral is a physics based schemes. So from these analysis for our North Indian Oceans, specific empirical correction like our scheme performed well compared to these 4 models with a 0 bias and the lowest RMSE. So we felt that the regionalized schemes are better for North Indian Ocean compared to the available existing schemes for the skin SST parameterizations. So as a summary, to summarize, we analyzed around 41,840 quality controlled INSAT 3DS and BUI SST matchups data. The mean skin and bulk SST difference is 0.67 plus or minus 0.56 degrees centigrade. So the skin and bulk SST difference exhibited a clear dependence on wind speed, net heat flux, and local solar type. Wind speed correction primarily represented a mean offset, while diurnal sinusoidal correction based on local time captured the dominant fraction of observed skin and bulk SST variability, with the QNet providing an additional but modest improvement. So results highlight that diurnal warm layer processor dominant in this region, driving the skin and bulk SST differences over the North Indian Ocean. So this study support future development of regional skin and bulk SST correction scheme for INSAT 3D SST. So this emphasizing need for regional skin and bulk SST correction over the North Indian Ocean. So these are the references I have mentioned. Thank you so much for all your attention.
Thank you, Soksan-san. Stay online, please. Okay, move on the next speaker, Dr. Yoshida, developing a framework for reporting reliability of coral temp SST. All right, please go ahead.
Good morning, everyone. I'm Momo Yoshida, a PhD student from James Cook University in Australia. Today, I'm going to update my progress toward developing a practical uncertainty assessment framework for the NOAA Coral Reef Watch Coral Temp SST. This is a massive, complex question we are trying to answer, and my talk today only represents the very first step, a tiny tiptoe into this big pool. Level 4 SST products, including Coral Temp, are subject to multiple uncertainty sources. Comprehensive uncertainty characterization requires access to intermediate variables generated during the L4 analysis. However, in reality, these variables are not retained due to stretch constraints. Why do these intermediate variables matter so much? Because they hold critical information on systematic errors. These errors arise from factors such as input data density, algorithm assumptions, including quality control and bias correction procedures, and background prior fields. These errors can propagate through the analysis and produce large-scale structure biases. As a result, end users who rely on level 4 products have limited insight into their spatially and temporally varying reliability. This lack of transparency is the exact gap my work aims to fill. Coral Temp is one of the most widely used level 4 products in marine science community. It provides a daily global nighttime-only SST at a resolution of 0.05 degrees. This product is called Coral Temp because the heat stress monitoring products derived from Coral Temp are specifically designed to track and monitor global coral bleaching. Coral bleaching is a process. Under heat stress, corals expel their symbiotic algae, zoos and scylla, leaving their white skeletons. Coral bleaching can lead to mass bleaching and even coral death if the heat stress is prolonged and or severe. This is a major concern because coral reefs support a huge biodiversity, protect coastlines from erosion, and provide food and livelihoods for millions of people. Uncertainties in Coral Temp can propagate into derived heat stress metrics, potentially influencing bleaching predictions, either missing a severe event or triggering a false alarm. Therefore, first characterizing the reliability of Coral Temp is important. In this talk, I'd like to especially focus on one intermediate variable called correlation map, which is related to spatial temporal data density, and explore how that affects the final analyzed coral temp. The data for this analysis come from the Great Barrier Reef in Australia. The GBR is a heavily instrumented coral reef region, providing data coverage across both nearshore and offshore. For the study period, I looked at January to April of last year. This time frame captures the critical summer window, which is the period we care about from coral bleaching perspective. This time frame also covers a diverse mix of both cloudy and clear sky conditions, allowing us to see how correlation map affects the final analyzed coral temp. The areas highlighted in cyan represents the coral reef pixels on the GBR, and the blue dots indicate the specific points where we have in-water temperature logger data available. To start with, let me show you first how the coral temp SSD compares directly to the in-water temperature. This is the 2D density histogram plotting coral temp against in-water temperature. The dashed line indicates perfect agreement. As you can see from the dense yellow and green clusters along that line, the two datasets generally align well. However, you can spot much cooler in-water temperature than the SSD on the lower right. These anomalies are likely due to massive monsoon troughs, where record rainfall drove cool terrestrial flood plumes into the inshore central GBR in early 2025, cooling in-water temperature while the satellite remained blinded by the cloud cover. Before moving on to the next figure about the relationship between temperature differences and correlation map, I'd like to describe what the correlation map is. During the data processing, the system evaluates local data coverage by sliding a window across the grid. It counts how many valid observation pixels exist within an 8x8 window and the 32x32 window, shown in this schematic by the cyan pixels as the valid pixels. Based on these counts, it calculates spatial data density, and the resulting index value sits somewhere between 8 and 32. In areas with a lot of input data, the index stays close to 8. Conversely, in sparse observation regions, the value grows larger, moving toward 32. This variable is used directly for correlation-weighted interpolation. It determines how far the system needs to reach out, spatially, to fill in missing data gaps. Here, the x-axis shows a correlation map grouped into bins with a step size of 1, with the y-axis tracks delta T, which is SSD minus in-water temperature. If you look across the plot, most of the bins from 8 all the way up to 30 show a very stable distribution centered right around 0. But in the final bin, where the correlation map is between 31 and 32, we see the entire box structure shifts upward, featuring the highest median, first and third quartile, and the upper whisker, and the lowest lower whisker, and the cluster of outliers stretching from 2 up above 4 degrees Celsius. We also looked at whether the duration of correlation map matters. Here, x-axis tracks the number of consecutive days that a pixel's correlation map remained at 31.0 or higher, and the y-axis shows delta T. Starting from 3 consecutive days, we see a clear progressive shift. The first quartile, the median, and the third quartile all gradually increase up to day 9. Beyond day 9, the entire distribution remains above 0 degrees Celsius with some fluctuations. This indicates that persistent high correlation map values have greater effect on the delta T than short-lived ones. What we learned from this pilot analysis is that magnitude and duration of correlation map may contribute to the reliability of coral temp SSD. However, as I mentioned earlier, this is really a fast tiptoe into a much more complex question. I fully recognize that there are many different avenues to explore to build a robust framework for reporting reliability of coral temp. First and foremost, I need to deeply understand how the whole system works. My immediate next step will be to trace down the analysis system codes to see exactly how one variable behaves alongside other intermediate variables in the algorithm. Second, we need to explore the effect of multiple intermediate variables on the final analyzed SSD. A major challenge here is that we must decompose our uncertainty sources. Isolating one error source from another is critical if we want to generate meaningful statistics. Importantly, this applies not only to the level 4 SST data, but also to the in-water temperature logger data we use for comparison. For instance, we need to separate satellite interpolation errors from physical local processes affecting the loggers, such as depth differences, vertical stratification, tidal cycle, and wind conditions. We also expand study periods and sites, specifically targeting where and when bleaching events happen. I'd like to appreciate UMETSAT and Copernicus for providing the support that allowed me to attend this symposium and meet and talk to global SST experts. And I also like to acknowledge my co-authors for their contributions. If anyone's interested in the significance of this work, here are the QR codes for the video and paper talking about more detailed implications for coral bleaching monitoring tools. I would appreciate any feedback, comments, or questions you might have, especially anything that challenges my assumptions and really makes me think deeper about this program. Thank you very much.
Thank you. All right, move on next speaker, Owen-san. Metadata conventions for uncertainty in SST product. Please go ahead.
Hi, I'm Owen Embry from the University of Reading, and this. Owen Embry from the University of Reading, and this is some work which I've been preparing with the colleagues from Reading and the UK's National Physical Laboratory. So, as you've mostly heard, measurement error and uncertainty error is not necessarily the same as uncertainty error, is the difference between our measurement and the true value, which generally we don't know, whereas uncertainty is a measure of how uncertain we are about our measurement. And as we've heard earlier, this is quite important, and we've got standards for how we should estimate and record our uncertainties from the Joint Committee to the Guide of Metrology, GUM, and VIM, but we don't have any common standards on how we can store this information in our files and pass it between each other and to our end users. So what we really need is a common standard for the metadata to encode this into our NetCDF files, ideally not just for sea surface temperature, but for any data set observed or modeled. And basically, it should be compatible with the climate and forecast conventions. So here I'm going to summarize a proposal we've been working on to submit to the CF Conventions Committee to do this. This work is an outcome of a meeting organised by the UK's National Physical Laboratory last year, which was held to address these needs for not just sea surface temperature, but climate ref, CMIP, OBS for MIPS, and the ESA Climate Change Initiative. I was part of a subgroup with my co-authors to prepare this proposal for the CF Conventions Committee. It considered the needs of metrology through the participation of the National Physical Laboratory, modelling through David, who is from the National Centre for Atmospheric Science, and I was representing observations. Probably the key thing about our proposal, we're not the first people to attempt to send such a proposal to the CF Conventions Committee, but we are, I believe, the first who've actually involved a member of the CF Conventions Committee in preparing the proposal. So we are hopeful that we will actually succeed this time. It's currently in expert review and will be submitted to the committee for approval later this year. As a bit of background, we're basically combining the existing work from NPL in their COMET toolbox, where they've taken a methodological approach to encoding fiduciary effects tables. Here's an example of the metadata that produced. And you can see it's basic, well, the toolbox is a Python program, and it's basically writing out all the Python information into the metadata. So it's very complete, but it's not following the CF conventions. So it's this time that approach would not be accepted. And I've also taken what I've done in the previous SST CCI specification. In that, we were specifying multiple uncertainty components, the total, the random, correlated, and systematic. In that case, I was recording all the important information in the sort of full text, comment, and long name, so it's human readable, but it was not machine parsable. In our proposal, we've basically added a new attribute to the data variable called uncertainty variables. This follows the same convention as the existing ancillary variables, where you just have a space-separated list of all the linked variables. An associated uncertainty variable will use the same dimensions or a subset of the dimensions of the parent variable, optionally adding one interval dimension if you happen to be recording your uncertainties as a confidence interval as opposed to a standard deviation or otherwise. The units of the uncertainty variable have to be consistent with the parent as you'd expect. So if it's Kelvin, then for the data variable, the uncertainty should also be in Kelvin or millikelvin or some variant like that. We do allow for relative units to be provided, so you can have uncertainty expressed as a fraction or percentage where it's appropriate. In terms of the uncertainty variables itself, we've specified several attributes. Two which are required are the coverage interval and the coverage probability. Then there's several optional ones which I've listed here. So the coverage interval, you specify how you're expressing your uncertainty, whether it's a standard deviation, a half width, or offsets to specify like the upper and lower bounds of the interval. The coverage probability tells the end user what our estimated probability that the true value is going to lie within the specified confidence interval. You can express the uncertainties either a difference or a relative difference. If you're using the coverage interval of standard deviation, then the probability distribution can specify if it's a Gaussian or uniform or other probability distribution. If you've got a standard deviation, there's an option to specify if your interval's like one standard deviation, two standard deviations via the coverage factor. You can record how you've come to your evaluation of the uncertainty, whether it's statistical or scientific judgment. Next, we've got the uncertainty component attribute, where you're providing multiple components of uncertainty for a single data variable. This has a special value combined uncertainty if you want to specify the total. Otherwise, it's effectively free text to describe what this component represents. And finally, there's the error correlation attribute, which, as you can imagine, is going to be quite a complex thing, given you can have a whole range of different error correlations. So the error correlation attribute has its own vocabulary, which is based on the existing CF conventions for cell methods. So there are three general conditions we can explain here. You can provide a complete and explicit error correlation or error covariance matrix. So that's supported. Generally, a parametric structure would be better, where you can define the correlation pattern using some named structure and parameters. And finally, there's effectively a text description option where you don't know the exact correlation structure, but you can define it qualitatively. So the syntax is similar to cell methods. So effectively, you list a set of dimensions that your error correlation is applying to, then either specify the auxiliary variable or a named structure along with the parameters. For example, here we've got error correlation that's applying to the latitude and longitude dimension. It's got a and it's using the bell-shaped relative distribution with a sigma of 15, whereas along the time dimension, we're assuming this is independent. So as an example for for an SST dataset, how this might look, I've adapted it to the Sea Surface Temperature Climate Change Initiative metadata. So in this case, we've got our independent uncertainty, tell it the units, it's a standard deviation, Gaussian, named it the uncorrelated uncertainty, and the error correlation in this case is simply independent. Below, you've got the locally correlated uncertainty. Most of the metadata is the same, but then you see in the error correlation attribute, we can say on the latitude and longitude, we're using the final text description version. So we don't have an exact null representation of the error correlation structure. So we're just telling our users that the length scale in the spatial dimensions is 100 kilometers, and in the time dimension, it's correlated on scales of a day. Finally, we provide the total uncertainty in a similar form, and just the key thing here is the uncertainty component is set to combined. Providing a total uncertainty is not required in the specification. In that case, it's up to the end user to combine all the provided components to give the total. And in the case where you only provide a single component, it is by definition also the total. So in summary, we've been working on some uncertainty metadata naming conventions, which should hopefully address the needs of both metrology, modeling, and observations. We've involved the CF committee from an early stage, and it's currently being reviewed by external experts with a plan to submit it to the conventions committee at the CF workshop this September. We're planning to use this as the basis to allow GDS3 to specify SST uncertainties in a CF compliant way. If anyone would like to look at the proposal or provide comments, let me know. We're accepting beta feedback until mid-July. Thank you.
Thank you. It's a time for question. Is there any? Please.
Thank you, Owen. Just a quick question out of ignorance. When we talk about standardization of uncertainties, is that somehow regionally dependent? For example, uncertainties in the high latitudes going to be standardized in different ways, and uncertainty in western boundary currents and uncertainty in coastal regions? Or is that, I mean, is that a relevant question at all?
So this is just sort of a CF conventions approach. So it's standardized in terms of the metadata we use to encode it. If you include a latitude and longitude dimension in your uncertainty variable, then you have your regional variations.
Okay, thank you.
Yeah.
Hi, Owen. Thanks for the talk. A quick question. So this metadata convention would apply to level 1, from level 1 onwards. And if you, I mean, how do you rely with space agency for the production of the different?
Yeah. So it can be used for anything level 1, level 0, level 2, 3, and 4. It's not specific to sea surface temperature or satellite data in any way. So it'd also be used for modeling data or entirely theoretical data. So the idea is it will submit it to the CF committee, and it would become part of CF conventions. So any data set that follows CF conventions could use this approach. What we would bring into GDS3 is just a a very small restricted subset of what the CF proposal would support.
Please.
I've got a question for Swapna. Is she online?
Yes, please.
Did you consider using the absolute temperature of the absolute temperatures as also an indicator or a variable in determining the bulk skin difference? And for those, this is slightly different, for those pixels that were close to the coast, did you consider the notion that it's possible that turbidity in case 2 waters could be causing reflections close to the surface and therefore double heating of the water column?
Yeah. Question, is that over? Can I answer?
Yes, please.
Yeah. As you asked, we used the GHRSSTs only covering the Arabian Sea and Bay of Bengal. We have not chosen the coastal buoys as far as our analysis is concerned. If you see that data slide, there only the buoys available in the Arabian Sea, in the mid of the ocean, and Bay of Bengal also considered. No coastal buoys were taken into our analysis, and all the buoys observations at 1 meter depth only considered. So in that analysis, we followed the strict criteria of 1 meter depth buoys, 1 meter bulk SST, and only deep ocean buoys, no coastal observations. And as you said, we have used this whatever skin SST, whatever bulk SST observations of INSAT 3D and this buoy SSTs. So we have made a conscious decision on this.
Okay. Did you consider the actual temperatures, the bulk,
Yes.
the temperatures, and see whether or not they were correlated with the skin bulk difference? In other words, was the skin bulk difference different at high temperatures versus lower temperatures?
Specifically, this we have not studied, but could you clarify the question? I didn't get exactly what you're asking.
So you're looking at wind as a variable.
Yes.
It's also quite possible that temperature is a variable. So,
Yes.
So there's no doubts that there is some decoupling of the skin bulk differences or skin
Yes.
bulk variables at high temperatures, whereas there's less or no decoupling at the lower temperatures. So,
Yes.
so temperature itself can be a variable.
Okay. This dependency of only temperature variability, we have not considered whether it is low or high. We maybe look into that. But as you said, we just saw the difference of skin and bulk SST differences with respect to all the parameters. But as such, within SST, how low temperatures, high temperatures are varying, that we have not considered. Maybe I will be looking into it.
I've got a comment for Momo. So the problems that you've got up at the up in the high temperatures with your matchups between the satellite data and the logger data are
Yes.
not. Sorry, this is for Momo. This is a different different topic.
Okay. Thank you.
They're not real. If you have a look at your data, you'll find that those loggers are almost all in the southern Great Barrier Reef, and they're all at depth. They're not right up near the surface. And it's because the southern Great Barrier Reef has a lot of cold water intrusions that never make to the surface. And they can be shallow enough, often quite shallow, and will be bathing your your logger data in quite cool water that the satellites can never see. So that's probably what that is. So that entire, that would be real. You could probably throw the whole lot of that away. So my suggestion is have a look at the loggers. You'll find that there's only a handful of loggers that are giving you those data, and just throw them away and use the rest of the loggers.
Yeah, I actually was going to ask, because, you know, where the corals experience the temperature is actually like the bulk, 2-meter depths or 5-meter depths. So I'm just not sure how I can why I can show away these bulk temperatures. Yeah, because you know what I'm trying to say. I'm just trying to head around you know, the temperature corals actually experience, and the DSW and the heat stress metrics derived from coral temp is actually using this foundation, pseudo foundation temperatures.
Understand, very easily fixed. The algorithms don't use temperature. What they use is anomalies. So you need to turn your logger data into anomalies and compare those with the anomalies at the surface. Don't try and compare the absolute temperatures. The absolute temperatures are interesting and worth doing, and that might be a chapter of your PhD. But most of your PhD should be concerned with comparisons of anomalies, not. And the question then is, are anomalies at depth, say 5 or 6 meters depth, correlated with anomalies at the surface? So trying to find some loggers on where you've got loggers up near the 1 or 2 meter depth and loggers down at the 10 meter depth, and asking the question whether their anomalies are correlated would be an interesting question. So you've got to try and nut out which of your loggers are truly representative of what the satellite is doing before you can determine whether or not the satellite's doing a good job of determining the temperature. So don't blame the satellite if you're using a logger that the satellite can't see. That's my point.
Thank you very much. No, that helps a lot. Thank you, William.
All right, almost we're delaying almost 10 minutes delaying, so we're gonna close here and then have a coffee break. We have a 25 minutes, but
it's going to be shorter, so we will come back at 11:10. Okay.
11:10. Okay, please come back to 11:10. Okay. Thank you.
Okay, Professor Reagan, can you hear me?
Yeah.
This is Ebuchi speaking.
Hi. So
Okay.
now I test
So
my screen sharing.
please start sharing your
So
screen.
you can hear me.
Okay. Okay.
Is
We
it
can
okay
see
now?
your computer. Okay, screen is shared, but it's not the full screen mode.
Uh, Now you can see my computer?
Yes,
You
but
can see
it's
the
not,
slide?
but it's not full screen mode. Yes, it's the top page.
Yeah. Would you please see again?
Yes, I can see your first page. And could you make it the full screen mode?
Let me see. Full screen.
Yes, nothing. Okay.
Is it clear
Perfect.
now?
Perfect.
Okay. Thank you.
Okay. Okay, thank you. Please stop sharing.
Okay.
Dr. Wimmer, are you online? Dr. Wimmer, are you online? Maybe no. How about Dr. Arbani, are you online? Maybe not yet.
Yes.
Dr. Wima, are you online?
Yes, I'm here.
So please share your PowerPoint slide, please.
Yes, give me a second. You start sharing?
Yep.
Oh. Okay. It's slow.
All right. Could you change the mode, presentation mode, please?
Yes.
Oh, yeah. It's not working.
That's what I was saying. It was a bit slow, sorry, to do the presentation mode. Cool. Should I leave it there because I'm the first one, or you want something else?
Will you say again?
Should I leave the presentation there because I'm the first one in this session anyway, or should I stop sharing again?
We can see that fine now, so you can keep sharing. So you can start.
Can I start?
Sure.
Okay, we have 3 more talks for session 5. I'm gonna start here. The title, Dr. Wima, title is Sensory GHRSST validation using the fiducial reference measurement service. All right, please go ahead.
Thank you. Hi, good morning. My name is Wernfrid Wimmer. I work at the University of Southampton, and I will talk about SLSTR-SST validation using FRM data. So the talk is starts with the data sources and the processing with it, the validation methods, and the results for the Sentinel-3 SLSTR data from 2018 to 2025. Then a short look at the annual results, and we also look at the individual data products, not just the WST, D3, D2, N3, N2, and some conclusions. So the data is used for this validation exercise is the SLSTR data from Sentinel-3A and B from 2018 to 2025. For the satellite data and for the in situ FRM data, the radiometer data from the GHRSST project, same data as Chris used for his L4 analysis. This is using it for L2 validation. And the MDP files are produced by Felix at EUMETSAT, thanks to Jean-Francois and the team at EUMETSAT, Igor and Gary. So files are produced SLSTR level 1B and level 2 data within 400 pixels of the matchup location, and GHRSST data within 6 hours of the matchup. And on the side there, you see a map of the GHRSST data in the archive. It's slightly biased towards the Atlantic. This is totally accidental. It's where we have the shipping routes. We try to expand it, but it's a cost issue. We need funding to do more ships and more operators around the world. The validation methods used were published a long time ago in the paper mentioned there, Wimmer et al. 2012. So the MDB files as produced by Felix get reanalyzed by us. We allow multiple matches per matchup location. However, that means we still only use one satellite pixel and one GHRSST data point. So those points aren't used more than once, but there's more than one matchup per overpass. And we validate all data products in the MDB files and for all CRISP quality levels 0, 3, 4, and 5. 0 means no quality level applied. But the results presented here are only for CRISP quality level 5. And in the plots shown on the next slide, we will see those matchup grades starting from grade 1, which is the tightest matchup window within half an hour and 1 kilometer, down to 4, which is within 6 hours and 25 kilometers. And these are the global validation results shown by year. The big blob is the median of the validation results, and the error bars are the robust standard deviation for that matchup window. So the colors go: blue is the tightest one, red is next tight, green, and yellow is the widest one. And you can see that because the error bars go generally up when you have the wider matchup windows. As the all data results, and then you have it split into day and nighttime results for different years. You can see 2021 and 2022, the data looks slightly less good, which is partially because we were quite heavily impacted on our amount of data we got during the COVID years, because ship operation wasn't that easy, access to ships wasn't that easy. So we had a lot less data in 21 and 2022, and these plots show the amount of data, again color-coded by the matchup grade. So the tighter grades get less data, and the wider matchup windows get more data. But yes, when you look for Sentinel-3A, the SLSTR on there, the distribution of those matches, you can see, yes, it's slightly biased towards the Atlantic, which is just where most of our ships operate, the ones we use for our measurements. If we look at the histograms, and the histograms, all three of them, the red line is the actual data, and the blue dots are what a Gaussian fit would look like to the median and standard deviation. In the yellow box at the top, you can see the median, the robust standard deviation, and how many data points contributed to the histograms. And you can see they're all quite nice. There's a little bit in the tail, but overall they're actually following the Gaussian fit reasonably well. It's slightly better at nighttime than at daytime, as expected. And if we do not just for the WST product, but for all products, the histograms, daytime to the left, nighttime to the right. Daytime doesn't have a dual 3 and nadir 3 because the 3.7 micrometer channel gets oversaturated, so we don't have that. And the dual 2 and nadir 2 product at nighttime are experimental because you have the nadir 3 and dual 3, and they're generally better. So on these scatter plots across the X, you have the different matchup windows, and on the Y-axis you have the data products. And you can see here that in general, grade 1 and grade 2B have narrow histograms than all the other grades. These are the ones where you match within a kilometer, so on the SLSTR pixel, they are generally producing better results. Also, you can see here that the one with the tightest histogram is the nadir 3 product, which isn't completely unexpected. Look at the same results for the SLSTR and Sentinel-3B. Slightly different spatial distribution is accidental because of ship operation times and satellite overpasses. Histograms very similar. Again, very nice, following quite closely the Gaussian distribution. Again, slightly more at nighttime than at daytime. Slightly more artifacts in the daytime results, but nothing to worry about. And when we look at the all data products across all matchup grades, again, as the nighttime ones look very good, and we will see it in a moment when we look at the actual numbers. The nadir 3 on STR and Sentinel-3B is really good. It's very tight histogram. And these are the numbers for the different matchup grades for the WST product, so not for all products, just for one product. And you can see there is hardly any median difference between the products, and the robust standard deviation is quite low. It goes slightly up from the tighter matchup windows to the wider ones, but you can also see that number of matches go substantially up from the tighter windows to the wider ones. And this is the point on the Sentinel-3B. Nighttime, we get robust standard deviations of 0.17, which is very good. We can also look at the statistics across the years to see if there's any trends. there aren't any. Yes, we can see more so on Sentinel-3A that there is a small bias creeping in 21, 22 in daytime. It's only there at nighttime. In 21 on 3A and 3B, this is because there were so few matchups through the ship's restrictions through COVID. So it's a data issue more than actual performance issue of Sentinel-3. And this is the data from the different shipping routes and different operators in our project going into it. And this also puts me to a slightly sad comment that all the blue data is MERI data from University of Miami and Peter Minette's team. And because of NASA funding shortages, this will disappear in the future. We're trying to see if we can mitigate it with other instrumentations on those ships, but we're still working on that. We haven't found a solution to it yet. All the reddish colors are ICERs, and the green color is only one, is sister from our colleagues at RAL. If we look at the results by data product in my dot and line plots, you see they all perform quite well, apart from the Nadia 2, which struggles a little bit more than the others, especially at daytime. But overall, they're all very good and conform quite nicely with what we expect. If we plotted these plots across the regions, this is in 2025, not for the whole time period. You can see there are some differences. Some are because there's low data volume there, and some are potentially real geophysical things. So we might have to look into it. I found this quite interesting in daytime one. This is data from sister on the Queen Mary 2. This is data from an ICER on the Discovery research vessel. They were going across the Atlantic, so it looks very similar, which points towards it might be a geophysical feature there, they're discovering there, but also you have to remember the data volume there is quite low, so there are very few data points to look into. So overall, the validation of SLSTR with FRM data shows very good results for SLSTR. There's virtually no mean difference at night and only a small difference at daytime. There are some differences in 2021 and 2022, which is due to data volume and ship operations. And the rust deviation is lower at nighttime than daytime and is very comparable to previous sensors like ETSR. There are some regional differences, and we'll have to check into those, but they're nothing to be too concerned about at the moment. And yes, we had some issues during COVID. And all the other results are available if you want to see them. Come talk to me. And last point is, this work has been recently published, and you can read it all there in detail in the remote sensing issue from earlier this year. Thank you.
Thank you, Dr. Luna. Stay online, please. Okay, move on.
I'll stop sharing.
Yes. Okay, move on. Next speaker, Dr. Albani. It's online. Okay. Please share.
Hello, good morning. Can you hear me well?
Yeah, please share your slide, please. Building more than 40-year advanced AVHRR global data through CEOS agency collaboration. Okay, please go ahead.
Thank you very much. So my name is Mirko Albani. I work at the European Space Agency in Frascati, close to Rome, and my talk is going to present the results and the status of some activities that we are carrying out at ESA in cooperation with other organizations to recover AVHRR data on a global scale. Let me first make a short introduction on the ESA's Heritage Space Program, which is an ESA-wide coordinated action, which is covering more than 150 heritage missions. Through this program, we are ensuring at ESA the preservation, the access, the curation, and the exploitation of data from heritage missions, which are missions not anymore in operation, but whose data has been acquired in the past and are still very useful and very important, for example, for climate applications. This is the list of Earth observation heritage missions covered through the program. As you can see, we have some ESA missions like EURES and ENVISAT, for example, which are fundamental to build time series with respect to current missions like Sentinels. But we have also data from third-party missions, including AWHRR. So all these data are archived at ESA, preserved, but also continuously improved and valorized to make sure that they are somehow aligned with data from newer missions. And also most important is to say that all these data are openly and freely accessible for all users through the ESA website. So all these data are open and free for all users. In the frame of the program, we have also a lot of international cooperation with other organizations, mostly in the frame of CEOS, which is the Committee on Earth Observation Satellites. And as part of these cooperation activities, we are also trying to recover heritage data from other organizations which might be not accessible at the moment for users. So we are trying to cooperate with other agencies like NASA or NOAA for the recovery of this heritage data set. So moving to the AWHRR recovery activities, we are performing a lot of activities in this frame since a few years. The first one is dealing with the generation of an AWHRR European master data set, so level 0 and level 1 data, which is based on the harmonization and combination of data from ESA, so acquired in the past from ESA, but also University of Dundee, SIDA, and the University of Bern. The second activity is, so this data set has been already recovered, is available, and we are still working on this data set to generate level 1C fundamental data records with an improved calibration of the sensors, geocoding, authentication, and so on. So an additional step to improve the initial data set. Then we are also supplementing this data set through the recovery of the 1 kilometer project, which was run in cooperation between ESA and USGS in the 90s. And beyond that, we are also coordinating with other agencies in the frame of CEOS Wikis to build a worldwide coherent AWHRR dataset, which is based on data holdings from CEOS agencies, but also on additional data holdings from other organizations that we are recovering at ESA, repatriating at ESA, and reprocessing and making accessible to users. The last point is also dealing with the transcription of legacy media, because we still have around the world legacy media containing unique AWHRR data, and we have at ESA a unique capability to perform the transcription of this legacy media. So we are also transcribing media that we have, but also helping other organizations in transcribing this media and unfolding the data there contained. I will now go with the 5 slides, one by one, for these different activities with a bit more of details. Let me also say that we have developed a tool to support these activities. This tool is basically generating KML files with available product frame coordinates. So we are able to ingest metadata from the AWHRR data available, and to generate graphs and heat chart to better identify gaps and to focus there on the gaps at our recovery activities. So the European dataset is a long time series which is today accessible through ESA with more than 40 years of AWHRR data from different platforms. This dataset has been derived merging data from the University of Bern, Dundee Station, and ESA. So we have more than 260,000 products harmonized and reprocessed to level 1B and 1C. And we are still working on this dataset to extend the dataset and also to improving the geolocation and the uncertainty estimates and the quality. Again, this dataset is accessible through ESA. You have the link in the slide, and openly and freely accessible for all users. As I was saying, we are also working on this dataset to generate a level 1C, which is an orthorectified product, fundamental data record in NetCDF format. This data set is being reprocessed using new software modules with an improved geocoding and auto rectification with respect to the original one, with the error propagation and a more accurate uncertainty estimates in the calibration module. So this is addressing all channels, tier and near channels over Europe, with also calibration techniques and correction to minimize the historical cross-calibration biases between the different satellites. And in addition to that, we are also extending the data set from 2020 to 2025 and to the late 70s, adding additional data from EUMETSAT and from SIDA and University of Dundee. But also we are extending this in the direction of Greenland and the northern areas through integrating new additional data set. In addition to that, in the same project, we are also recovering data from other regions across the world. So from Argentina, received from the Servicio Meteorológico Nacional de Argentina, from Kenya, South African Space Agency, from the 1 Kilometer project, and from other sources. So this project will be completed in the next quarter, and the publication of all these data sets through the ESA systems is expected by the third quarter of 2026. This is another fundamental component of this data set is the global 1 kilometer data set. This was
sorry for interrupting you. Only 2 minutes you have.
Yes. This is an important campaign that was implemented in the 90s in cooperation between ESA and the USGS. So there were data sets acquired worldwide at ESA network stations, at USGS network stations. So these data sets were not accessible to users so far. They have been fully recovered. The data from the ESA stations are now accessible through the ESA websites, and the ones from the USGS stations will also be accessible in the next quarter. So this will provide a 7-year global data set from 1992 to 1991 to complement what is already available around. And these slides shows the data set which are available on EUHRR worldwide and which are being addressed in this international cooperation through WIGIS. The one with the green circle are the one available through ESA. As you can see, we have a full coverage of Europe, but also we have many other data sets covering, for example, South America or Africa, which have been retrieved by ESA in cooperation with other organizations. The temporal and geographical coverage of this data set is unfortunately not homogeneous, as we have a scattered time coverage and the geographical coverage. So we are still trying to fill gaps by recovering additional data sets. In blue, you have data from other agencies, NOAA, for example, or ISRO or XIRO, where we are cooperating together in the frame of CEOS. Take into account that from 2008 onwards, we have a 1 kilometer full global coverage available at EUMETSAT. So the effort that we are doing in this framework is to recover data before 2008. And my last slide is showing some transcription activities that we are doing. We have several data sets still on heritage media, optical disc tapes. As an example, we recently received from the University of Hawaii 500 tapes with unique data acquired between the 90s and 2000 over Hawaii, and we are proceeding now with the transcription of all these data sets, again, to then reprocess them at ESA and making them available through our websites. So that's all for my presentations, and in case of questions, this is my email address. You can reach me, but please also reach me in case you are aware of additional data sets which are available locally in some archives and not accessible to users, so that we can try to help for the recovery for the global worldwide user community. Thank you for listening my speech.
Thank you for Dr. Albani. Stay online, please. We're gonna move on the final speaker for session 5, Dr. Gunn. Yeah, please just right at the high-end one, the COC test to near real-time skin SST retriever. If you're ready, please go ahead.
Thank you. Good morning, everyone. I'm Lei Guan from Ocean University of China. Today, I will give talk on HY1E COCTS2 near real-time skin sea-surface temperature retrieval on behalf of the team. My co-author, Dr. Li, is now is my former PhD student. He's now working at National Satellite Meteorological Center as a postdoc. Dr. Ye and Dr. Jiang are from National Satellite Ocean Application Service. And this is the operational agency for China's satellite, ocean satellite. And the HY in Chinese, Haiyang means ocean. The HY1 series is for ocean color and temperature observations. The first two HY1 satellite, EA and 1A and 1B, are for experimental satellite, which was launched in 2002 and 2007. And the first operational satellite of H1C was launched in 2018. HY1E, the new generation Chinese ocean color observation satellite, was launched in 2023. The instruments on board the HY1E includes COCTS2, PMRS, CCI2. The local time of HY1E descending node is 10:30 a.m. And for COCTS source width is about 3,000 kilometer. And the nadir spatial resolution is about 500 meter. There are 3 infrared channels for SST observations, which centered at 3.7, 10.8, 12 micron. And here are data we use for algorithm development, including COCTS2 level 1 data, ERA5 data for atmospheric radiative transfer simulation, IQUAM data for validation of the HY1 COCTS2 SST, SLSTR level 2P SST data for intercomparison with COCTS2 SST, and OSTIA data for as a reference SST. The SST retrieval algorithms are developed using atmospheric radiative transfer simulations. We use Motron for the simulation. The representative atmospheric profiles of ERA5 are selected according to the characteristics of the atmospheric parameters. Simulated brightness temperature of the 3 infrared channels are obtained by applying simulation. The SST retrieval algorithm are derived by using simulated brightness temperatures and scan SSTs of the representative atmospheric profiles. Cloud classification and quality flags determination are performed. For SST algorithm, we use NLSST. MCSST is working as a first guess SST. We develop both split channel algorithms and triple window algorithms. The coefficients are regressed for different latitude band. And for each band, 2/3 of simulated data are used for fitting and 1/3 for evaluation. For the evaluation test, the results show the daytime and nighttime split algorithm has an RMSE of 0.37 Celsius degree. Nighttime triple window algorithm is 0.18 Celsius degree. For quality flag determination, is performed according to the infrared channel brightness, temperature, land, and ice mask, cloud mask, retrieved COCTS2 SST and some texture features, and so on. Cloud detection is performed by applying the spectral and the texture features of infrared and visible channels. We set totally 6 levels for quality flag. So 5 is the highest quality level. And this is the result of SST, global SST, acquired on August 3, 2024. And the left one is the daytime split window SST. Middle is nighttime split window SST. right is nighttime triple window SST. Here is another example for the level 2 SST on July 27, 2024, which shows the image of different quality flags. We evaluated the near real-time SST product during the period of July 16, 2024 to July 16, 2025, for about 1 year. We compare the product with in situ and the GHRSST. We set the special windows of 2 kilometer, 4 kilometer, and 9 kilometer. The temporal window is about 1 hour. Actually, there is not a significant difference between the different special windows. So for the comparisons with IQOM high quality SST, the statistics show the bears of minus 0.17, and for RST it's about 0.5 Celsius degree. For daytime and nighttime triple window SST, there is positive bears about 0.15, and the RST is about 0.4 Celsius degree. And here is a scatter plot of COCTS2 versus IQOM SST. And the bottom one is SST difference against latitude. We can see there is no significant latitude dependence. And this is a result.
You have 2 minutes.
Okay, this is result of comparison with SLTR-SST. You can see for the daytime and nighttime split window SST, the bears is almost 0, and the RSD is about 0.5 Celsius degree. For nighttime, we have a positive bears of close to 0.4 Celsius degree. And this is a difference against latitude. So now we come to the conclusion. We developed the algorithm for HY1E COCTS2 near real-time SST using simulation with a set of ERA5 representative atmospheric profiles. For split window algorithm, the bears from minus 0.2 to minus 0.17, and where compared with SLTR-SST, bears is close to 0. This indicates the consistency between the skin SST product of COCTS2 and the SLSTR. And for nighttime triple window, we have a positive bears. Actually, the calibration accuracy of 3.7 micron channel will be further investigated. So future work will extend to the evaluation of longer COCTS2 SST time series and conduct validation with in situ skin SST measurement. Thank you for your attention.
Thank you. All right, now time for the question or comment. Is there any question or comment? All right. I have one question for Dr. Wimmer. The nighttime mean difference is very close to 0. That it's very impressive, but there is still a finite spread in the match up differences. So do you have an estimate of how much of the nighttime RSD comes from the SLSTR retrieval uncertainty or FRM uncertainty and match up representativity?
No. We have to look into that again, matchup uncertainties of the whole process, but we haven't done that at the moment. So I don't know how much comes from the chip-on radiometer and how much comes from the SLSTR for that value?
Thanks. And we have a question from online participant.
Helen, you can.
Yes, hello, hi. My question is for the speaker before last about AVHRR, HRPT 1 kilometre data, stitch data archive. Sorry, I'm not sure of the gentleman's name. Is he still online?
Yes, I'm here.
Yep, hi. I saw that you had a circle over Australia. Have you been collaborating with CSIRO there? Edward King has and the Bureau of Meteorology have a stitched archive of data over Australia and Antarctic continent dating back to 1991, and they have raw data in a different type of format back to 1985. Have you been talking to Edward King at PSIRO in Hobart?
Yes, absolutely.
Oh, great.
Absolutely, yes. In the frame of CEOS Wikis, we are in coordination with Edward. We know that they are transcribing media and trying to consolidate and recover all the data that they have over Australia, which is exactly the same exercise we have done over Europe. So we are exchanging information, exchanging software. So we are in touch, and every Wikis meeting, which is happening every 6 months, we have a meeting. We have a dedicated session on AVHRR where we exchange information and status of the different activities. So absolutely yes.
Right. So of course the processing is different of the data at the Bureau of Meteorology, and it's still happening right now. I am actually retired, but I did lead the project up until 2 years ago. Helen Beggs is my name. Sorry, it's not on my screen there. But I wondered, are you planning, I mean, because the processing is different, so the uncertainties will be different. Are you planning to somehow combine the data sets, or will you process the raw data yourself from Australia?
That's a good question. At the moment, we are not planning reprocessing of the Australian data. So it is we are trying to reprocess data from minor archives and minor additional data sets, for example, the one we got from Argentina or from the University of Hawaii. For the major data sets like the Australian one, we will have to try to find a way of harmonizing in brackets the data sets. This is one of the next steps that we are planning to have. We have, for example, put together a presentation which is describing what is the format of the different data sets available at the different agencies to try to make this sort of comparison of the different data sets. So to have an harmonization step, and then an additional step will be to try to make all data sets discoverable through the CEOS infrastructure so that the user can enter CEOS and find all AVHRR data globally.
Oh, that's
so
fantastic.
Work in progress.
Thank you. Good luck. It's a big job.
Thank you.
It's good to see it's happening. Thank you.
All right. One more question from online participant. Oh, I saw, yeah.
I saw a hand raised, but I think they asked for it.
Yes, I have one question to Leguan about the HY1E data. So it's not clear to me, the processing you presented, is it the official agency processing, and are the data available? Are they in GRIST format?
Thank you. Actually, it's already operational running at the agency. They have delivered the level 2 data. I suppose the product at NSOIS are not in GRIST format. Dr. Ye from the agency have submitted an agency report in the meeting material. There are the website and the product description.
Okay, thank you.
Thank you.
All right. Is there any short question? No? Well, I would like to move on the discussion. Okay. I would like to open the discussion with a broad but practical question. What should GHRSST prioritize next? Best SST retrievals or stronger independent validation or more usable uncertainty and reliability information for users? So is there any comment? Please.
Hi, I'm not sure if this is an appropriate question to the group, or maybe I'm just too remedial, but the onboard shipboard, the shipboard radiometers, what kinds of challenges for the infrared come into those measurements? What are you concerned? What are you concerned with? What are you controlling for? I know for ocean color, for example, there's like a lot of things you have to throw out before you can use it. So I just wonder if there's a good sense of that, and then if they would be. I'm just thinking we're putting ocean color radiometers on some of the NOAA ships, and if there would be an opportunity to put some of those IR instruments on NOAA things.
Anybody have a comment?
Should I answer that? Yes.
Please.
Renfred Wimmer here. It depends which instrument you're talking about, but it's a lot simpler than the ocean color radiometers to use them. The instruments are self-calibrating, so they look after themselves more or less. You don't need to clean anything, don't need to do anything while they're deployed, so they're fairly straightforward. Mirrors are slightly bigger, ISOs and sisters are slightly smaller. They take about 20 watts of power and run for 3 months without needing much other than power and a good look to the side of the ship. I mean, that's about it. It's fairly straightforward compared to ocean color.
Do you have, Christopher, do you have a comment on that?
Well, just to say thanks for that intervention, Veronica. We should follow that up with you if there's an opportunity there. Yeah.
Yes, I agree, indeed. We should take opportunities where we can work together.
Is there any, oh, please.
So I think there are several reports have shown the uncertainties of the SSTs, and especially we also have a session, the Marine Heatwave before. So many people are doing extreme events using SST as it is. No uncertainties have been counted within the calculation, even definition. So I think more, yes, we also see Dr. Yoshida had proposed one reliability on the coral temperature. I think it's a really a crucial issue to let more researchers and even decision makers to think the satellite SSTs are still some gap between, especially for the extreme events. Yeah, yeah, that's all I want to say. Yeah.
I agree that. Is there any comment? I'm not going back to the question about the individual, the observation. I mean, the MUA already included the in situ data, and it's just using the as an independent observation needed to validate. So what kind of strategy we need to have, or to just promote MID observation, or what? What do you need? What we need to do? Maybe yes.
I think looking forward in time, it would be great to have a wider geographical spread of radiometers, which is why I was interested in Veronica's intervention, because they measure the skin, which is what the infrared satellites are fundamentally measuring. So that's really important, and the work that Fred has done on characterizing the uncertainties through GHRSST means they are a very useful reference, I think. But we saw that there's a limited geographical distribution in some way. If we are talking about the past, my feeling is that the data of reference are the Argo system. They're not numerous enough to have a huge impact on analyses, but they are numerous enough to quantify uncertainty and validate the uncertainties that we're adding to products, not only at level 4, but also at all the other levels as well. And I think that's a very useful role they could fulfill for this community, but it does require that we don't use them for other things. So we keep them independent. And so I would suggest that data producers who are using them within their processing chain should think about whether they should, in future, revisit that choice. Of course, it does depend on other in situ observation networks being maintained, because that's far from guaranteed, as was discussed before, where this is something we also need to be paying close attention to.
We recently had a discussion about the top layer of the Argo floats, and there's, different ones that do different, so we were talking about putting into our in situ monitoring system some quantifier about labeling at what depth was the top, because if you're just default taking the top, you might not be getting what you think you're getting. So we're talking about identifying that quantitatively somehow, so you know what you're going to get when you pull it. No, Andy, you're shaking your head no.
I'm pretty sure we know.
I was just going to say that's
the top depth is in the metadata, so you can know what depth you're comparing. Yes, you can.
I was just going to say that's a processing issue for IQAM. That's all it is. That the information is there. We just have to put it in, which we know. So I think it's being fixed. So,
and it used to be that the top depth tended to be between 5 and 10 meters for all of the floats. Of course, more recently we have the ones that go closer to the surface, which is extremely helpful. But even at 5 to 10 meters, we know the circumstances under which that's very tightly coupled to the surface. It's not all circumstances, but we can identify which ones are.
And it's helpful to have diurnal warming models and things like that to go between the surface and 5 meters. Yeah, exactly. Yeah.
You have the whole profile.
Yeah. At roughly 1 meter per resolution, and basically they shut the pump off at half an atmosphere below the surface to stop contamination of the salinity sensor, but they do unpumped measurements all the way through to the top, basically. So, which is roughly, it's 1 decibel sampling, so that's roughly 1 meter. So, Chris, are you suggesting that L4 producers should please go back and redo their analyses without including Argo? Is that sort of what you would really like them to do? Really just come out and say it, go on?
I mean, scientifically, yes. In practice, that's, you would have to have other motivations as well, I feel.
I mean, yeah, I mean, why not to run it more than once, as an experiment? Why
yes,
not?
Yeah, on an experimental basis, if that were done, that would be extremely instructive. Yeah, for maybe a year.
Yeah, okay.
Actually, I'm not worried about Argo. I worry about the ship-based data. So especially for the ship-based data, sensor is much more less calibrated than the Argo, I think.
But I think that one issue about Argo float is that when you want to validate that there's basically the location of Argo float is depending on the ocean current. If you want to have issue data, but there's no Argo, that always happens. So maybe we need to have another robust solution to have issue data. But now I don't have any idea about it.
Yeah, actually, there is an advantage to the Argo network in that they do tend to pop up in places where drifting buoys don't go because they're not being driven around by the surface currents. So that's one of the reasons, as well as their intrinsic data quality, that they are a very good reference.
Please.
Yes, maybe just to echo a bit what has been said until now on the use of radiometers. I guess it's been discussed earlier this week. Could be interesting also to recall that maybe shipborne radiometers gives us more chances to travel across structures and frontal features. So it's also useful to validate how SST is capturing structures and gradients.
Maybe that to understand fine scale phenomena that not right now I'm analyzing a SWOT data, the surface water and ocean topography. That might be useful to understand that the summit scale features or filament. So that's the opinion. Or any other comment? Oh, please.
With DMI, within an Horizon project, we are moving the ISAR a little bit around, and we're planning to install the ISAR in the Aqua Alta Oceanographic Tower in the Adriatic Sea. And the plan for the next year is to bring the DMI ISAR on the Italian research vessels, try to capture filaments and vortices in the Ionian Sea. That's the plan. So that's just an update. Okay.
Thank you. Thank you. It's great news. Okay. Okay.
Perhaps another point that we should consider is that there is an increase on number of ferry box on the ship research vessel, and this ferry box measure all these ferry box has a temperature measurements, and this also can be used in addition. Obviously, Argo allow us to monitor area in which we have not in general the ship track. So this is a very key important point. If we look to the presentation of Chris today, the radiometer data set are very accurate, but are along specific track and not cover the entire of the ocean, while the Argo is more, if I look, I think a map of the Argo or coming from is much more distributed. Obviously, there is a problem because the accuracy could be less. Not often they have the temperature at very high shell of layer of the ocean, but I think a tentative to use Argo to make an evaluation it will be very important. For level 4.
Oh, please.
Yeah, a quick comment. Siemens has been invited, the Copernicus Marine Service has been invited last year at the Euro Argo committee asking feedback. And as SST-TAC, we provided some suggestion as to possibly reach the surface, increase the sampling depth of an argo up to the surface. So any suggestion, comment that can come out here at GHRSST could be shared and reported through the European Argo Committee. Thanks.
All right, thanks. Looks like almost time is up, right? Is there any one more comment? No? Oh, okay. Okay. Last, please.
It's more of a question actually. Maybe it's not a very clever question, but have you guys also considered commercially available, satellite data for using it as a reference? I mean, maybe to use it as your operational SST product improvement is not what the agencies want, but to use it just as a reference independent source.
Is there any comment? It's commercial satellite means small satellite. So usually not, that is not calibrated, right?
Yes, I'm not sure that the commercial infrared missions that currently exist would be accurate enough for us.
All right. I want to close discussion here. So thank you so much for enthusiastic discussion. So we will move on the next session. So thanks so much.
Hi, so let's start with the last session of this GHRSST, which is on advances in computing, artificial intelligence and cloud computing for SST observation and products. We will have now our keynote speaker, Prashant Kumar from the National Institute of Technology of Delhi. Then we will go to lunch and then resume the session after lunch. So whenever you're ready.
So, thank you. Good afternoon, everyone. So today I'm going to talk about a little bit about physics-guided climate foundations of AI models. So especially when we talk about like SST or any other variables, so we cannot take out from the artificial intelligence in the coming time. So because it has a significant role to regenerate the data as well as predictions. So now basically as we talk about the oceans, so it covers basically 90% of the heat of the climate system, Earth climate system, and it also has different, we already know that SST is not just taking the observations of the oceans, it also predicts climate variability like ENSO, IOD, and it also associated with the marine heat waves and ocean atmosphere interactions, all are connected with that, which has significant impact on the global data-driven approaches as well as extreme events. But however, the existing SST products we have in present and the forecast forecasting system, but it still struggle to represent the extreme events. I think last session also that person talk about that we are able, it still has a difficulty to capture the extreme events, regime transitions, and long range dependency, especially prediction uncertainty. So all these three things still we are working on. And so basically the deterministic approaches on with uncertainty quantifications, long range climate memory, as we already know that El Nino is very major climate variability when we talk about the SST, and it has global climate impacts around the globe. And so it's still, there is several numerical weather predictions and some basic machine learning tools also there to predict the accurate El Nino predictions. But somehow we cannot able to predict the intensity still very accurately, even like 6 to 12 months ahead. We will see the transitions according to the changes in the sea surface temperature. So here we are trying to predict the SST using this model and then see that whether we can able to capture the imaginations, what exactly the ocean and atmosphere interactions. So as you said, the recent literature about the ocean warming and climate impacts, AI for the SST constructions, and there are several AI models is there which has a higher super resolutions using transfer learning and high-end advanced machine learning models is there. And further, we can and further this you can see the data-driven 3D ocean state estimations for eco monitoring is also there, and which can there is some literature related to the ocean chlorophyll predictions. And recently this is our paper in which we have like predict the ANSO forecast using the multitasking machine learning models. And this basically using this not only just different tasks like single task, due task, and then using the explainability of the SST, and then we have do the probabilistic forecast of that particular El Nino. And these are the challenges which we are facing, like the multi-scale spatial temporal complexity in the weather. So when we talk about the weather, it is not a linear phenomena. It is a very highly non-linear phenomena. It contains a lot of mathematical equations also. So sometimes we just physically understand the system, but we also understand that how they are mathematically connected, and the limited observations, data gaps is always there, like cloud covers. We already talk about the satellite thing, and then still there are challenges related to that. And the regime transitions like ANSO event, marine heat wave, IOD events. So these events sometimes unable to capture the simple numerical weather prediction system. So the physical consistency and uncertainty in quantifications, long-term ocean memory. So how we can capture, because when we take the high resolution data, also we talking about temporal, also we are talking about the long range. But when we all summarize together, then there is a very heavy data sets, and we need very you can say high-end GPU or TPU is also there. So all these things we can combine, sometime generalizing the climate model and training and future climate predictions. So still there is a distribution shift, and emerging extreme reduce the model robustness. So we will get the predictions, but again, the extreme is a little difficult to predict. And then operational and scalability, that I have already the high computation cost when we talk about high resolutions, high temporal resolutions, and even though we can go to 3D, or if you can say 3D ocean also, so it is very heavy data sets. And when we run the model, sometimes we lose the robustness. Maybe we get the prediction. So these are the challenges. I think we all are working to somehow to resolve these problems or the challenges. Yeah. So the key objectives basically in this that first learn the ocean climate memory. because ocean also has the memory for daily, monthly, and annual, decadal. We already have the decadal variability, annual variability, seasonal variability is there. Okay, so we cannot simply we cannot just preserve the only annual memory and then predict the seasonal, or just preserve the seasonal memory and predict the annual. We have to be very careful when we are taking the seasonal anomaly or daily anomaly, or you can say annual or decadal variations. So all are different things. And developing the generative AI climate framework, so it must be not just based on the black box that we use the data and then we can predict. So it also have some physical informations about the data. Even though it is SST, but we already know there is several agencies, they have SST data with different resolutions, and this preserve the physical consistency is very important. That how we are taking this physical consistency and then improve the forecast skill. This quality predictions of uncertainty. So we have to quantify that how we can reduce the uncertainty. That is the very big challenge. And how we can work that advanced next generation GHRSST products, because they are doing really well. Or because whenever we are using most of the paper data, we are using different products, but this is the other next task is that if we can help in somehow to improve maybe resolutions or predictions or data generation, that would be very great. So, so this is the data framework in which we can see that the data overview and the seasonal source informations is the temporal coverage, variable ability, and spatial coverage is there. And this is the data statistics which we have used. And these are the applications for forecasting like ANSO, IOD, and PDO, and marine heat waves, ocean forecasting. So as we already know, whatever machine learning model we can apply, unless we do not have a good information about the data, or we do not have a good input data to the model, we cannot able to predict properly. The data information is very important whenever we talk about the future predictions. So if data is little bit, not, I'm not saying not correct, even little bit bias with the observations. So we have to consider all the different type of data sets, and then we will observe whether what physical interactions with the atmosphere and ocean, other parameter also, then only we can able to apply some machine learning models. So the next question is, can the ocean remember? So how we can see that the memory can be preserved, exploring the climate memory through the global SST anomalies. So here we can see there is a evidence for the ocean memory and the climate variability, and how they emerging extreme event hotspot across the globes. And then if we putting the SST, that how it can take those global hotspots as a extreme events, and how model understand all these hotspots and try to explain all these variability. So this is the physics guided ocean GCM model. So this is the general structure of our model, in which we have taken this input data source SST in a different daily scale, seasonal, monthly, all. And this is the model, general model architecture, spatial encoder and temporal embedding. This is the extract the spatial features. This also convert the spatial feature into the spatial temporal features informations, and this will give the climate memory transformer. As I already told you, the ocean, we will also not consider just a data, we also consider ocean as a memory. So it can record the previous record, extreme events, hotspots, all the things it can consider. And then further it will identify, okay, this is the extreme events for ENSO in the Pacific, or this is the extreme events for the Indian Ocean as IOD or PDO for decadal scale, and IOD and ENSO, interannual variability is there. And then it will use the forecast decoder for the same variabilities. Now, this is the output features, and this is the training. So we also looking for the loss for the robustness all physics informed loss, consistency, climate consistency, and total loss is there. So these are the key features. So it has like long-term ocean memory, capture the global spatial temporal dependency, and adapt the climate regimes dynamically, and physics-aware data-driven hybrid and high-resolution global SST forecasting. So these are the key features in which we try to include like as possible to get the robust predictions. And so these are the comparative studies for the evaluations with different machine learning models. These are some state of the art and some advanced model like SST transformer, hybrid transformer, CNN transformer. This is our Ocean GCM. So we found the little bit, the accuracy has been improved using different skill metrics. And we found this just simple SST forecasting performance. Now, if we look for the marine heat wave forecasting, so we can see that. And if we simply see anomaly correlation coefficient for long horizon forecast, so what we did is not that when we take the input data. Okay. So when we took the input data, so basically different when we have to understand that. Okay. Also, we have to understand that whether we are predicting the extreme event, or we are simply predicting the marine heat waves, or we are predicting the ANSO, or we are predicting the IOD, or what exactly we are predicting. So we have to understand the model accordingly. We can't just say predicting the SST, then it can predict the ANSO, IOD, or other extreme events also. So we have to focus, either we are predicting the marine heat wave, or we are predicting the some other type. So this is the answer is nitty quantification, reliability, and this computational efficiency also we need to take care. And so this is the things in our model we are take care. So these are the further skill long horizon prediction analysis forecast skill. So long horizon forecast skill. So this particular model is performed well as compared to the other models. So again, this is the lead times. As we increase the lead time, that the RSM is decreasing. This is the forecast skill versus the persistent and other skill matrix analysis. So overall, the point is that we should, whenever we are talking about a machine learning model, we are not talking about simply that we are not checking one dimension scalability. We have to understand that our model is performing better in a different skill matrix. And then we see, okay, maybe sometime RSMA is good, but it may be not the right indicator for the models. We need to check another skill matrix. Taylor skill score is there, mean absolute error is there, some cosine similarity is there. There is nowadays several skill metric is there. So you can't take all, but you have to choose very cautiously that which skill matrix has the physical significance in terms of either you are predicting the SST or you're predicting some other variable. So you have to be very careful to choose the skill matrix. So now this is the SST forecasting performance comparison. So all different type of errors we are having, this root means RSME, MA, Pearson correlation, and other type of skill matrix is there. So we so we check not only just what we have to look all the parallel models in the current recent time, and then we found whether your model is performing well or not, and on that basis you can say the model may be providing the robust results. So this is the ground truth for marine heat wave detections case studies there. So we can see this is the ground truth, and this is our Ocean GCM predicted marine heat wave anomalies with around this 83.8% F1 score. And this is if we taking a CNN baseline. So we have to see the intensity capturing very well by this. And further, we can see the marine heat wave detection matrix also in terms of all three CNN, convolution, LSTM, and transformer, and Ocean GCM. So we can simply say how this precision and recall or different skill matrix, how it can work. So this is the case of ANSO. In case of ANSO also, we're taking another case study at the ANSO and IOD climate variability forecasting. So here also we can say this particular model performing good and showing as the lead month increasing like 3 months, 6 months, and 9 months. Of course, as you increase the lead month, the accuracy will be decreased in the machine learning models. But overall, it can give the robust predictions. This is the long-term climate trends and regime shift analysis is there. So my point is that it is not that we cannot simply focus that we are predicting SST, but we have to predict the SST in a different dimension. Like sometime we have to look at the ANSO point of view. Sometime we have to look at the long-term predictions trends. Sometime we have to look at the marine heat wave trends. So we cannot run one model and then it can predict everything. You have to train your model accordingly what exactly you want. And you have to provide the memory to the model with the same way. Then only it can give you the better accuracy. If you put everything in the black box and you run the model, you have a lot of models in the market, and then just put, and it will give you some forecast. It may be also give you some accuracy based on that. But whenever some extreme event there, it cannot able to tell you that, oh, this could be the marine heat wave events. It may say, oh, there is a temperature there, but he cannot recognize because there is no memory in the model. So that's why it is important. We have to focus that which event we want to predict. So this is the applications of the SST applications in a different way. ENSO, IOD, PDO, marine heat waves, climate change monitoring regime, safety analysis, next generation GHRSST products, ocean atmosphere teleconnections, climate variability, extreme event predictions, and it can have a very strong even fishery and the ecosystem management, and this all maritime navigation, coastal risk assessment, disaster preparedness, and climate resilience, climate foundation for AI Earth system, and digital twin ocean future climate simulation. So there is several applications when we talk about the
You have 2 minutes.
Okay. So this is okay. The conclusion basically. The ocean memory learning, physical guided AI, and improved forecast skill, extreme event intelligence, and next generation GHRSST product. Okay. So this is the reference. Thank you. Thank you very much for the talk. Thank you.
Thank you very much. Since we have like few minutes before go to lunch, if you want to do 1 or 2 quick questions, is that okay? Yes, Leah?
Many thanks for the presentation. It was very intriguing. My simple question is, if I understood well from your presentation, you make an evaluation, your capacity to predict respect to other artificial intelligence method. Do you have any evaluation respect to the prediction of the global ocean circulation model that are available, that are based on data simulation and primary equation?
I think global circulation model, we haven't predict related to that. We are more focused on the like ENSO, IOD, and SST based extreme events, especially focus on Indo-Pacific Ocean. Mainly we are working. So GCM we haven't done yet. Yeah.
No. Because I think it will be very interesting to compare the performance of, in general, of artificial intelligence model respect to GCM. And make this comparison respect also to the computational time and the power consuming of the two methodology.
We are working on one paper in which all this you can say future GCM models, different semi-6 models, and based on that the uncertainty has been reduced, especially for using transfer learning for SST forecast. So like semi-6 models, they have some range of the predictions for 2100 or more. So we are working on that, and we see that that using the transfer learning, that uncertainty is improved using machine learning. So,
okay. Are there any other questions?
Okay.
May I ask something myself?
Yes, yes.
I didn't get it. Maybe you said it, but which data set is your ground truth? And how long is your training data set?
So basically, we are taking 20. We are taking basically 26 year of data set, 2005 to 2026. I think 2025 December, and then in that whole durations we are using for 70% data of the training and 20% for testing and 10% for prediction. Overall data set, whatever it is. So we are not simply taking that like a seasonal. So that's why saying we have to seasonal, annual, as well as monthly data sets. So first we have input the daily data as well as making the seasonal and monthly and annual data. Now we have identified that ANSO and IOD, it is annual climate variability. But some like if you are looking for the PDO, so it is a decadal variability. So we are using all these data sets in a different time domain as well, based on their intelligence. So model understand, okay, ANSO is coming like annually, it may be neutral, it may be up, but PDO come decadally. So even though you give the monthly data set, so sometime it may not understand because it is a very long variability. So model have to first understand that what type of data it is getting, because SST is plain. So if you are simply giving the mean, so we have to understand that whatever we are giving to the.
Okay, so the just coming back to the Claudia's question, so the ground truth you are considering is the 10% of these data sets. So you are using different data sets to retrieve to use them in a different temporal scales, if I got it properly from your answer. So, and then you just keep the 10%, and this is your ground truth. So you are trying, this is the data set that you keep for the validation of your model.
Yes, 10% data for the.
And just a very quick, otherwise I asked you the question for after lunch or after the session. I didn't get properly, I don't know, maybe it was clear for the presentation. So your objective is to develop one method that predicts all these indicators that you were saying, or you have to develop one model per each?
Yeah, one model for each.
Okay.
Yeah.
That's
why, because you can't make one model which can predict everything. So if my interest is to predict the marine heat wave, so I will train my model accordingly, not with the ANSO or IOD point of view.
Because you need to train the lost function for each. Okay, that's clear now. Okay, thank you very much.
Thank you. Thank you.
Okay, let's thank the speaker again. And now we go to lunch and we come back at 2. Thank you. So let's start again with session 7. Thank you, Chris. We have now our next speaker, Ed Armstrong from NASA JPL. So Ed, the floor is yours.
Hey, thanks a lot. Thanks a lot. Good afternoon, everyone. Again, I'm Ed Armstrong from the NASA Jet Propulsion Laboratory. I'm going to talk to you about what we've done with regards to cloud data optimization, and this is part 2. I did a part 1 last year. There's actually, I was thinking about it, I've already introduced or talked about this topic for like 2 previous science team meetings. The first one in Canada, I just kind of introduced the principles. The second one last year, which was in the part 1 title, that was actually, we had some working examples and we had gone a little bit more beyond R&D. But as you'll see with part 3, is we've actually moved beyond that. We actually have a full catalog. We have an operations system, and we're very active, involved in building this community of both producers and users. So in my talk, I'm just going to review the principles of cloud data optimization. We call them virtual data stores, or VDSs. You'll hear me use that acronym a lot. And the accomplishments is that in this catalog, now we have 12 PODAC data sets virtualized, including several GRIST ones. We've developed a level 2 approach. So previously, this works very elegantly with gridded products, but we've adapted it, had some success with level 2. And we've documented all this in a chapter on our cookbook. So you can find working tutorials, both how to read and even how to build these virtual data sets. And there are several use case examples I'll kind of show you. I'll talk a little bit about our next steps with a new iteration of this technology, the new generation called IceChunk. Previously, we were working with Kerchunk. And then talk a little bit about the user uptake, community building, and the operations we're building, and then wrap up. So this cloud data optimization through virtualization, we're really after building an ecosystem to encourage faster and more repeatable science. And there's basically three pillars. There's the actual data virtualization, where we're creating very lightweight JSON representations without copying or transforming the file. So one data set has one of these JSON reference files. And the idea here is very easy for the user access, and there's no additional overhead on the data producers to implement this technology. Extremely lightweight. And yeah, we want to promote optimized data access, allow the user to retrieve only the data required for analysis, as shown in this little schematic here, and optimize the compute and memory only on those portions. And you just rinse and repeat for every new data set, every new parameter you want to start working with. And so as this little cartoon shows, we're trying to get away from software that operates on a file-by-file basis, where you need to open every single file instead into a system where we already know where the positions in the file that we want to access are, and we just go and grab those and ignore everything else. All right, so virtualized data through virtualizar. And virtualizar is the library that we use to create these things. It's actually not the technology that does it. And virtually v1 is the preferred Python packages for our activities, because we're in the Kerchunk world. It's an open source Python package that allows us to do the data conditioning and pre-process the data files and create these very lightweight JSON reference files that essentially all they do in this JSON file is map the internal byte locations of the data to the ZAR data model. So when you open up one of these things, you're actually looking at the ZAR data model representation of the NetCDF time series. We don't change anything in the underlying data. We just create references to it. And of course, we're using Kerchunk under the hood. Virtualizar version 2 has these additional capabilities to produce ice chunk that I'll talk about. It's a little different approach, more efficient, newer, but has its own kind of sets of problems at the moment. All right, so as of this month, we've created virtually reference files for 12 data sets that cover the spectrum of our parameters, so SST, SSH, ocean, wind, currents, and salinity. The idea is that we have something for every type of users at least to start using and touching on. And these JSON files are, of course, in the cloud, in the S3 bucket. All of our NASA data is in the AWS cloud. And of course, these reference files, these JSON files are there. But the thing is, there's two types of JSON files, the ones that support in-cloud access, just the S3 links, and then out of cloud, where they have the HTTPS links. So you don't need to be inside the cloud to use these things. They work in and out of the cloud. And as I mentioned, most of these are for the level 4. Level 3 and level 4, but we have 2 example success stories of virtualizing a level 2 data set. All right, this is just kind of a list of what's available right now. So, we've done everything for at least one virtual data set per parameter. So we have something for wind on the top there, the remote sensing system, CCMP, and we got some echo stuff that has some temperature. There's a couple of GRIST data sets in there, including the MUIR 2.5 and the MUIR as well, on a shorter time series, and the GRIST Ostia reprocessed is in there, the longest time series record going back to 1982. And then a few other ones in there. There's salinity, there's something for GRACE, and then these 2 level 2 you see at the bottom there, one for wind, and the SWAT level 2 low resolution Karen. All right, so where do you find these things? We've actually made the locations of these reference files, and I'll use interchangeably reference files or chunk manifests, or sometimes talk about the JSON file. You find these on the dataset landing pages for the product. We've embedded them in this section called the related URL. So you go to data access, and these are some of the related URLs or nodes where you can actually go get the data and and use it in like an open DAP. But yeah, you'll see there the third and the fourth row, or the fourth and the fifth row down, have the virtual collections. So they have the pointers then to both either the HTTPS or the S3 version of the JSON file. And yeah, you just click on that and grab the link, and that's what you're going to embed in your Python code to call these things. I'll show you in a little code snippet here in a second. All right, I told you we've had a success with level 2, so we've tried level 2. It's a little bit of a different animal. This technology works great for gridded products that have consistent coordinates. They all neatly kind of stack on top of each other. Level 2 is a different animal, but we've had some successes with at least 2 data sets. In this case, it's the SWOT. But some of the requirements for level 2 is we call the candidates have to be well-behaved with repeatable orbits. That's kind of the critical thing, and SWOT does have that. And what we're looking here is a SWOT view of a SWOT aggregated data set for a small snapshot in the ocean. What we've done is we've actually created new variables inside the VDS. In this case, it's either the orbit start time, or it could just be a consecutive granular ID in the case of the SWOT data. That's the variable you use to catenate on, because you have to have one variable. Usually it's time. You have to have one variable that you're going to concatenate the entire time series on. But of course, you need also consistent dimensions and chunking. So I've tried this approach with a few GRIST level 2 data set, and it was not successful. That's with the Modus Aquaterra L2P and also the AMSR L2P, because there's some granules in there where the coordinates or the dimension sizes just vary for a single or a handful of granule, and then this approach breaks. There might be technological solutions to this once we get into ice chunk, but that will help us solve this problem. But really, one of the key requirements for successfully adapting this technology is that they are consistent dimensions and coordinates, and it just makes it much, much easier. All right, this is just a few example applications of things I've done or produced that you can find in this cookbook chapter, and you can find the link to that cookbook chapter in the presentation if you want to go back. But yeah, on the left-hand side, I got this query on the Earth Data Forum about some user. I think he was working for a magazine or a paper, and he said, tell me something about the decadal temperature changes in the Northeast Atlantic, which is also one of the areas in the world that's undergoing rapid warming and climate change. And I kind of gave him a gray area answer. I didn't have really anything on hand, but then I thought over the night, I have like a VDS for the MUIR 2.5 data set that has an SST anomaly inside it. So I was just, with a few lines of code, I was able to quickly whip up a nice multi-decadal image of the warming in this area, and just, doing some simple pixel by pixel averaging of the anomaly values, and, and generate a simple plot that demonstrates that strong warming on the order of 1 degree per decade in this region. So that's something you can do very quickly. And once I had thought about that, I executed it within a few minutes. This other area, a plot shows another example of kind of more an interdisciplinary approach of using 2 VDSs, both wind and SST, and looking at the time series and changes of the strong upwelling and the strong winds in this small area in the Gulf of Tehuantepec off Mexico. And this is another example that I showed that also, runs I would say in several minutes, because you have to do like a regridding step and stuff like that. But there's all kinds of cool, like interdisciplinary things you can attack very quickly and very easily, and share them with other researchers. And there's very little, really no data conditioning that needs to be done to execute on these things, which is great for sharing science results. All right, this just shows a little code snippet of how to do this. And this is just all really simple and straightforward stuff. I think this is actually coming out of this, one of those comparison images I showed in the Gulf of Tehuantepec. But okay, just have a little code snippet to log in with your Earth access credentials, because you're going to need to read that to access data on in the NOAA Earth Data Cloud. And then you establish some credentials to access, establish a S3 file system to do accessing the data. So, okay, 1, 2 conditioning steps. The third step there is actually we call the lazy loading, to actually open the data set and get access to it. So there's actually a little subroutine that does hide some of the little bit of the complexity, I would say, but it's pre-canned. It could be used just as is. And the argument is the link to, I believe, the JSON. Yes, it's a link to the JSON VDS. And then we're just going to, dump the lazy load contents in a few seconds. It loads, right? And we have access. You see up there, it's 11 terabytes. So we have access now at our fingertips. The entire time series of the Ostia reprocessed. And the last little box here is the one that does a little subsampling, it does some subsampling or subsetting, resampling, and averaging for both the SST and the wind. But I'm just showing the SST loading, but you can see the wall clock time at the bottom there. I think this was another multi-decade or a 10-year exercise. And I can't remember if I was running this locally or in the cloud, but if I was in the cloud, I was using a bare bones EC2, and it took less than 6 minutes. All right. Yeah, I think I'm coming to the ends here. We have been looking at Ice Chunk, which is developed by this company called Earth Mover. It's next generation cloud native storage engine for multidimensional data. And this is an evolution from Kerjunk. It has some excellent capabilities that we're interested in, including versioning and being able to do data appending that we can't really do elegantly with this Kerjunk model. We can't append, we have to actually recreate the Kerjunk VDS every time new data, every time we want to increase the data content. Some of the other things is that, yeah, there's consistent reads. It's, you know, Outbrace almost like a little database. And what we've seen that it's more performant. It's actually faster, it's more efficient, and the chunk manifests are small. These chunk manifests that I talked about, these JSON files are on the order of like 10 to 100 megabytes. But once they get bigger than that, they get a little bit unwieldy. And Ice Chunk is much more efficient, more performant. It's actually more like it's not a JSON anymore. It's like a Parquet file. It's like a directory structure. It's like a little mini database. Okay, it works great, but there are some current limitations that it doesn't allow HTTP access and the passing of the NASA Earth data login credentials to read the chunks. So until they figure that out, it's only in cloud access, which I think is a limitation, because we find a lot of users are out of the cloud, right? They're on their laptop at home or in their office. They're not necessarily in the cloud, but that's expected to be resolved soon, probably by the end of the summer. We're already in communications with the developer in the Virtually Czar2 community, which is again the library that's used to create these Ice Chunk stores. We have created 2 PODAC trial data sets for in-cloud access. That's the SASE Echo, and again, one for the Ostia reprocessed version 2. And if you want to learn more about this too, there's another cookbook chapter just on Ice Chunk stuff. All right. Yeah, I think I'm going to go through this kind of quickly. It's just another example of how you can use this. There's a company called Development Seed. One of my co-authors, Amy Barchauskas, graciously created an Ice Chunk version of the Muir, the entire Muir 1 kilometer data set. It's a little bit unwieldy to work with because it has inconsistent chunking, but she was able to kind of hand wrap it and massage it and make that available. It's actually in the NASA Earth Data Cloud. If you're interested in using it, let me know. I actually have a notebook. But in this little exercise here, we took Jorge's paper that I think his poster actually showed some results of this, of looking at a gradient analysis between Ostia and the PODAC MUR. And so we were able to recreate some of those plots he showed in his poster or his paper in a matter of just a few minutes. We were on a pretty powerful EC2 at that time, but to produce these plots and kind of drill through the entire time series, which I believe was like multi-decade or maybe 10 years. I mean, we really reduced the time to do this from hours to minutes. And the hours comes from the fact that you got to go get this data. And to get that data and subset it, it's going to take you several hours to do that, especially for the Muir. It's very data dense. But the beauty of this is that you can just get the data you need. And if you want to iterate of your study area, you don't need to go read down the data. You just lazy load it with different spatial dimensions. And so, yeah, there's actually a notebook that demonstrates that there's a little bit of trick to read both an Ice Chunk and actually the Ostia is a Kerchunk, but that notebook shows you the trick how to do it.
Ed, please wrap up.
Yep, we're going to wrap up. So we've been involved with some community building. This is we've held a webinar, and what that shows is just some usage statistics. And we built an operational system that's based on Airflow and Kubernetes. So Airflow is the orchestration. And we're running this in the cloud. We can just basically target a specific time series with a short name and just let it run very quickly, and it produces a VDS at the end. Okay, so quickly as my summary, we have 12 existing VDS in the Kerchunk model, both in and out of the cloud is where you can use it. We've developed a novel technique for virtualizing level 2. And of course, all this is carefully documented in our cookbook chapters and our usage recipes. We have done a few native ones for the GHRSST, Ostia reprocess and Muir, and we've investigated Ice Chunk. That's what we see as a way forward. We're going to solve these technical issues very soon. And yeah, we're interested in growing the community and creating many more VDSs, and actually really within NASA contribute to some enterprise solutions. And as part of that, harden our Airflow operations and migrate the VDS structure to Ice Chunk. So thank you very much.
Okay. Okay, thank you, Ed. Let's move on to the next speaker, Lucas Amezquita, coming from the Copernicus Regional Center for Latin American and Caribbean. Yeah, you did a lot more than you should. But we are good people. So Lucas, whenever you're ready, I will give you the 2 minutes note.
Okay.
Thank you.
Hello. Well, hello everyone. My name is Lucas Amezquita. I'm from Copernicus LAC Chile. I want to acknowledge to Marina Hernandez, my colleague, and Jaime Ortega, my scientific director. And of course, thanks to the support from EUMETSAT and Copernicus that let me be here with you today. I'm gonna talk you about the regional high-resolution sea surface temperature product for coastal applications and climate monitoring in Latin America and the Caribbean. But first, I think that I have to tell you about Copernicus LAC Chile, if you don't know yet. The Copernicus Regional Center for Latin America and the Caribbean is a joint initiative between the European Union and the University of Chile, executed by the Center of Mathematical Modeling. Its purpose to bring the capabilities and benefit of the Copernicus program closer to the countries in Latin America and the Caribbean, strengthening the scientific and technological cooperation. How we do that? We have 3 main areas of work. The first one is infrastructure, where we have a high performance computer for that let us process the Earth information or Earth data information in a very strong way. And we have a storage capacity that we are using right now for mainly Sentinel. The second area of work is data in situ strategy. Is that we are building a platform to articulate different actors, producers of in situ data, users with we are trying to introduce the standardization in there. So I think that is very useful. And the last area are the key services that where we have different focuses. For example, land cover land use, urban atlas, coastal monitoring service, sargassum, biodiversity, and now atmospheric modeling. I work in the coastal monitoring service. And in here, we provide products based on Copernicus Marine Global, of course, with a methodology that is traceable scientific, is traceable and support the analysis, the management of coastal areas, and we are focused into public institution, private sector, and academia. In this service, right now, we have published just 2 variables, sea surface temperature and chlorophyll concentration, both just for 1 year, 2024, in a monthly resolution. We chose these 2 because we, with a scientific committee, we believe that are important to be the first 2 ones due to importance in different biogeophysical processes. Specifically, the sea surface temperature product, in all the steps of the reconstruction follow the GDS standards in order to the physical traceability, interoperability, of course, and the comparison with the main ocean monitoring systems. This is the workflow in very simple words. We have 4 steps, bringing from level 2P until level 4 that is published. We start with level 2P with information from different sensors in different platforms. We using the SLTR from Sentinel-3, the VIRS from NOAA 20 NPP, and the AVHRR from method B and C. And we start applying quality control where we filter the clouds. We only use night observations and select pixels with a quality level 4 or 5 and with winds over less of 6 meter-seconds of wind. Then we make a regrid for 2 kilometers in order to make the standard resolution for all the sensors. Then we made a daily composite for each sensor and applied harmonization using Sentinel-3 as reference. And then we reached the L3S level using the median, a sensor prioritization for each pixel in order to increase the coverage. Finally, we applied the model. The model keep the pixels with information, and we use as input an observation mask for the pixels that have value and which don't have value. And at this level, we are working on monthly. We applied a land sea mask, bathymetry, distance to the coast, and the historical SST fields from the Copernicus Climate Change Service. Then the result, we compare with IQAM dataset. There are a sample of the institute data that we use. The comparison against IQAM dataset show low bias, strong correlation, and RMSD between 0.47 and 0.71 Kelvin. The comparison we are doing with Ostia, and we can see here that we have a close large-scale agreement. We are able to identify the thermal gradients, and the mesoscale structures are very similar. This is how the product sees in the platform. You can access it through that link. That is all the area that we have from Mexico to Drake Pass, reaching Easter Island and the Northern Island from Brazil. As I say, it's just for 2024 right now in a monthly resolution with 2 kilometers. You can enter here and download the data in ANSI format and SAR. What makes us different from the global product? That we have a geographical focus just for Latin America and the Caribbean. We try to improve the spatial resolution for compared with the global products. We made a variable selection for prioritize what we want to develop. I said before that the variable selection we are doing with a scientific committee, but it's very important to say that we work articulating all the countries on Latin America and the Caribbean. So we try to consider their opinions. For example, last week we made a presentation and a workshop in Barbados, Caribe, where participate a lot of people from different countries, a lot of institutions. We use the platform. I think that we get closer to the real needs of the countries. So it was a very good experience. Anyway, this year we are working on updates and improvement of the products, specifically for sea surface temperature and chlorophyll. We are optimization. We are on an optimization phase for the algorithms, and that's gonna let us make a historical production for 2018 to 2025, improve the temporal resolution. Right now we have a monthly resolution, but at the end of the year, we expect to have a daily resolution for sea surface temperature, 8 days composite for chlorophyll. And also we are working in new products, like a set of variables of ocean color, sea level, sea surface salinity, and a special high resolution chlorophyll that is limited only for the coastal area. The methodology that we use is now, we already sent a publication to be reviewed, is submitted. So we hope that in next month we have news about that. Thank you very much.
Thank you very much, Lucas. So we will move on with the next speaker. Should be online. Aina, are you there?
Yes, can you hear me?
Yes, very well.
Okay. You're going to share your screen, I suppose. Yeah. Give me a second.
Yeah.
Okay, can you see it now?
Yes. Can you put it in presentation mode? Yes,
Yep.
now it's perfect. Go on.
Okay, so I'm Aina Garcia. I come from the Institute of Marine Sciences in Barcelona, and this is part of my thesis, which is called Infrared Cloud Masking, Multifractal Turbulence Theory, Meeting Machine Learning. Well, basically, just a bit of introduction. Cloud masking presents quite a lot of challenges in Earth observation in infrared. Some of them are listed here. For example, they can introduce biases by introducing these badly filtered measurements in climate studies. They are also a critical problem in tropics and polar regions and coastal and upwelling zones because we have quite a lot of clouds in the poles, as you can see in the free sky pixel graphic in the right. Then we also, there's a need of a large time series in order to train models and compute lookup tables in order to calculate these cloud probabilities. And also let me stop the slide, current methods like machine learning or thresholds or kind of every method in the literature, they are prone to false and true, false positive and negative retrievals, which can introduce this kind of undermasking and overmasking of information that, well, I mean, we should maximize this information and we should minimize the cloud information. So in this work, it's a work in progress, but the objectives are to improve the detection near the cloud edges, work towards a climatology-free cloud masking algorithm, meaning that we should be able to retrieve these clouds with single images, and then maximize the clear sky measurement retrieved and while minimizing the presence of clouds. In order to do so, we work with the Sentinel-3 Level 2 product, SST product. We only consider daytime measurements over the sea. And this methodology, basically, we propose two new techniques. The first one is using the singularity exponents as a texture channel. I'm going to explain later what these exponents are. And using a Gaussian mixture model as a machine learning approach to detect these clouds. But yeah, again, we can check other algorithms later. And we validate this by doing first a visual assessment, and then we use singularity spectrometric, which I will also present later. And basically, we have worked with 3 data sets. One is the original level 2 Sentinel-3 mask. And then we have trained the Gaussian mixture models, both with the singularity exponents and the local standard deviation, which is the texture that they use in the official cloud mask. So what singularity exponents are, it's basically a representation of this turbulence that we see in the fluids. This representation is unitless, meaning that it doesn't matter at which scale we're working, we are gonna have them always in a fixed range. And as you can see in the pictures on the right, they also define they define better than the standard deviation these frontal areas of the temperature. And well, if we see here again, I'm going really fast here, we can see that the relation is actually real between both variables. So yeah, as I was saying before, the singularity exponents have some advantages over using these kernel functions like standard deviation or mean or whatever function that wants to be used. First of all, it enables us to work at pixel level because it doesn't have you don't need a radius to compute them. They are computed at every pixel, so we don't have this blur effect or like extended pixels that might be filtered. So it gives us a higher precision. Again, it's unit independent, so they are normalized globally, so it doesn't matter which variable you're studying, which variability these measurements show in the open ocean. And finally, yeah, it's more outlier robust, which makes it more stable than the standard deviation. And on the right, we have a picture showing that they really are capable of detecting these cloudy structures that we can see over the ocean. This is from Molchi, but can also be applied, as I said, to any channel. We're going to use the Gaussian mixture, also a bit of introduction on that. Gaussian mixture basically works by separating your data, your measurements, according to Gaussian distributions of the data. So basically it pairs all the possible variables and calculates this kind of clusters based on the density of their histograms. This is just for illustrative purposes. This is not made on real data, but it explains basically which variables we're using for our models, which is the difference of TV between the channel 1 and channel 0 from Sentinel-3, the singularity exponents or the local standard deviation in case we're training the other model, and this is surface temperature. So yeah, this is some preliminary results. At the moment, results vary quite a lot between one image and the other, so we need to study this. But yeah, we can see two examples on the left and on the right. The first row is the Sentinel-3 official mask. The second one is using singularity exponents, and the third one is using local standard deviation. And as I said, it's the same texture that they use in the official mask. So I don't know if you can see my cursor. Can you see that?
Yes, we do.
Okay, thank you. So basically, we can see that both with the Gaussian mixture, we're able to remove these cloud edges, higher temperature that we have here. But in the case of the local standard deviation, we have extra filtering both here and here. But yeah, overall, and here we have we are able to retrieve values that the original mask couldn't, so that's also good information. But yes, we can see this was just a little test to see that the results were actually made sense and it was not filtering just random stuff. So they are quite consistent between the tested methodologies. And then finally, just to wrap up a bit, we use the singularity spectrum metric in order to assess the dynamical properties. Basically, it acts like a kind of PDS of the singularity exponents. And what it does is that it should theoretically follow this red line here. So when it follows this line, it means that the fluid that we're studying is following the turbulent cascade, which the ocean should. But when we have clouds mixed in, this is like another kind of turbulence introduced to our signal that shouldn't be there and will deviate this red line. So we tested that with our data. We did, I think it was 6 months from 2024 that we trained. And these are the curves that we get. The black one is the theoretical one, the one that every dataset should follow if the filtering was perfect. And then the orange is the original Bayesian cloud mask. The blue one is using singularity exponents, and the purple one is using the standard deviation and also the Gaussian mixture model. And as we can see, When we use both Gaussian mixture models, we obtain the curves closer, meaning that we are filtering better these clouds. Also, yeah, both outperform the current mask. We should investigate more why the standard deviation still gets closer, but I think that it's because it's over filtering, so it doesn't have to be like a good thing. I mean, it's better because there are less clouds, but also we are losing quite a lot of sea surface temperature information. But yeah, we need to also try to tune these models to obtain the best result possible. And then let me finish with this conclusions and future work. I've separated them by the thing that climatology free by using only one image. But by what we've seen, it should be feasible to mask those clouds using single images. The results are promising. GMM performs well most of the time, but as I said, it's not consistent. Some images are not looking good, and yeah, we cannot rely on checking that every image looks good. So we need some tuning or some kind of other more sophisticated model. And so this is for future work, tuning this model or just exploring different segmentation algorithms that might work better and can make the best of these singularity exponents. Finally, yeah, singularity exponents as texture channel. We saw some advantages like it's unitless, it's sharper than the kernel functions, and it's resolution independent, which generalizes better these cloud masking algorithms that should not be optimized for a single sensor or a single satellite. One of the bad things about them is that they use a global normalization, and then it means that we need some kind of balance between the cloud and the sea in order for it to distinguish both classes correctly. But luckily, globally, it's pretty stable, the percentage of clouds, so we should be good with that. And yeah, and finally, I think that we should see improvements with other segmentation algorithms that are pixel-based instead of distribution-based. And yeah, that's it. Thank you.
Thank you very much. Aina, we will take questions after the next talk. So if you can stay with us a little bit longer, it would be great.
Yeah, sure. Sure.
Okay. So our next talk is online also. Maxime, are you there?
Yes, I'm here. Can you hear me?
Yes, very well.
Okay, great. I will share my screen.
Yes. So Maxime Béchamp from DMI?
Yeah, exactly. Can you see the screen?
Not yet.
Not yet. Okay.
I retired yet? No, we cannot see it.
And now?
Now, yes.
Okay, I'm going to presentation mode.
Yeah,
Is
perfect.
it okay now?
Go on.
Okay, great. Thanks for inviting me to give this talk. So yes, I'm Maxime Beauchamp. I'm a research scientist at the Danish Meteorological Institute. This is a work that has been mostly led by one of my internships there, Maël Le Guillauzic, about end-to-end data assimilation based on AI architectures of global sea surface temperature and ice surface temperature products. So this is more or less a follow-up of a presentation I made last year in GHRSST as well regarding a similar SST product focused on the North Sea Baltic Sea. And we extended the method and application on a global strategy for both sea surface temperature and ice surface temperature, trying to fill in the gaps of satellite observation to provide L4 non-gappy reconstructed fields. So typically, this kind of problem was or is still addressed by data assimilation, where, as you can see on this scheme, you try to combine observation with some gaps, of course, due to clouds or spatial coverage of the satellites, with physical information or Gaussian process-based information in sort of optimal interpolation strategy to provide as outputs a combination of the two informations and provide a non-gappy sea surface temperature fields. And this is done, I don't know if you can see my mouse, by generally minimizing some sort of variational cost that aims at minimizing some compromise between the observation and your prior deterministic model information. And last year, I presented you an AI model based on a data assimilation strategy, which is called 4D VARNet, previously developed on SSH experiments 3 or 4 years ago, that basically start from the same minimization problem as data assimilation, so minimizing a compromise between an observation cost and a prior-based regularizer, except that we change a lot of things in this approach because we will not use a deterministic model anymore. We will learn a neural AI model as a prior in the regularization cost. So this is the first thing to do. And we will also learn a minimizer, a solver to speed up and to optimize these cost functions. So two things to optimize in this AI model, the prior formalism and the minimization of the problem. So this is more or less what you can see in the pipeline on the left-hand side here, where basically starting from gappy inputs, you will learn two operators, the priors, the minimizer of the function, and you will give as output a non-gappy L4 fields. So as input, we use 20 years of data of gappy satellites information. I will describe that a bit more in this slide. So typically we start from independent channels from SLSTR, the ASTI-derived products for polar regions, AVHHR, and also passive microwave information that we complement with additional masks regarding the land, the sea ice fraction, the spatial location, and the temporal information on all this information that will give as inputs to the neural networks to provide the non-gappy fields as outputs. So since we are dealing the problem from a data assimilation point of view, we introduce also what we call a data assimilation window, which means that we will try to aggregate all the information from the satellite over a given temporal window. And in this specific application I'm showing you today, it will be 15 time steps, so 15 days, which aggregated on all the satellite channels, it's quite a big number of information, 120, plus some complementary information then given as inputs of the neural network. And of course, when you train an AI model, you need a target to train your model on, to learn something. So what we use here as a ground truth to train the AI model, it's a fusion of SLSTR for the sea surface temperature and the ASTI-derived product for the ice surface temperature. And this product combined will be used as target of our AI model to optimize the loss function I've showed you before. So this is for the main inputs of the neural network. As I told you, we have two networks to optimize. First, a prior in the variational cost function. It's here a very basic neural network, a typical CNN, used to just project the information and optimize it to help us to optimize the cost function. So this is for the first thing. And you have next the second neural network you have to learn, which is the solver in charge of minimizing the cost function. So as I told you before, it starts from a data assimilation formalism. So it will take as input an observational cost, a prior cost, and based on automatic differentiation tools that are provided within any AI-based framework, now we can have access to the gradient and learn how to optimize this cost function. So we could obviously do that without any neural network, but it's probably better to do it with a neural network. So we compute the gradient of the variational cost. And instead of computing a classical gradient descent, we learn a gradient model, taking as input the same gradient. And why do we do that? Because it will learn how to be much more faster than a classic optimization scheme. And it will also help you, because you're training your neural network, to escape the Gaussian and linear assumption you're using in traditional data assimilation. So in the end, with this kind of model, you can optimize and reconstruct non-gappy output with only 5 or 10 iterations of your variational cost functions. And after you run this entire pipeline, you will be able, as outputs, to provide non-gappy fields. So I show you here a sequence of 5 days, and the output of the algorithm will be a non-gappy fields for the SST and IST product. One big question is that we are only using satellites here. We don't know exactly what are in the gaps we want to fill in. So how do we train the neural network? So we use a self-supervised strategy, meaning that starting from observation with gaps, we will create artificial gaps, meaning creating observational data even more sparse than they are really, and we keep it the rest for training and validation. So this is really a training on pure observational product. And one key component that I started to present also last year on the North Sea Baltic Sea is that we introduced what we call a multi-resolution scheme. And why are we doing that? Because running this kind of model on the entire globe will be very difficult because the data set is huge at high resolution. So we decompose the domain into small patches at high resolution, and we will embed intermediate patches for an intermediate resolution, as you can see here, and the same thing for the global resolution. So in fact, we will embed 3 different resolutions in this algorithm. And what do we do in the end is that the entire pipeline I showed you before, it will be run 3 times, 1 time at coarse resolution on a 50 days time window, a second time on an intermediate resolution on a 9 days data assimilation window, and a last time at very high resolution on the last 5 days. And all these scales are more or less adapted to the actual space-time correlations of the dynamical processes we want to catch on. And here are some outputs. So you can see the 3 resolutions we try to embed with obviously the gaps present in the satellites and how the algorithm is able to fill in these gaps at every resolution. And as you can see, it seems to work. It seems quite physically consistent with what we would expect from any data assimilation or optimal interpolation algorithm. You can see here how it works with the global patching strategy. So as I said, we decompose the domain into small patches. So for the intermediate resolution, this is how it works on the entire globe. And you can see that from this complete gappy field on the entire Earth, we are able to reconstruct everything. And here you have basically an output starting from the non-gappy fields at the highest resolution available in this project, so 5 kilometers, and how it is able, the algorithm in the end, to reconstruct an L4 product that is quite realistic and competitive with classical assimilation algorithm. And in the end, a key aspect is that this multi-resolution algorithm and this patching strategy that has been developed made this algorithm quite easy to run even on modest hardware. You don't know a very big computers and GPU capabilities to run this kind of model, which means that now we are able to run all this model in only 2 minutes on a very modest GPU and a single one, so that it's completely realistic to use this kind of approach to in the end, replace our traditional algorithm for delivery production to Copernicus, for instance. Thanks for your attention, and if you have any questions, I'm staying online.
Okay, thank you very much, Maxime. Okay, so now it's time for questions for all the talks that we had, even for the keynote before. Are there any questions? Yes, Jeff.
Yes, it's a question for Ed. With what you showed with the virtualizer, do you think there is still a need to offer and recommend open data and thread services, since it seems you can do the same thing with this wizard data sets with even better performances?
Oh, yeah. Sorry, I just tripped right there. Could you please repeat the question because I wasn't listening carefully?
Okay. So what you showed with this virtualizer multidimensional data sets, do you think that we still need to offer and recommend OpenDAP and thread services since you can do pretty much the same thing for data subsetting with better performances?
That's an excellent question. I would say we still need OpenDAP because it has a lot of legacy users. And one thing about the modern OpenDAP in the cloud, they actually, as part of the production system, produce these what's known as these DMR++ files that are also very, they're like mini chunk manifests, right? That point to the files that actually OpenDAP uses to subset data that's in the cloud. And with these DMR++ files, you can also do virtual aggregation techniques. So just having that capability as another way to do virtualization, besides having the web GUI and the API, I think is enough to justify continuing using OpenDAP.
Okay, thank you, Ed. Other questions? Chris, there is a microphone there. Yeah, great. No, that one is fine.
This is for Maxime. That's very interesting talk, Maxime. I didn't quite understand. You seem to be using SLSTR and ASTI as your target, but SLSTR was still gappy. So how can you use a product that's still gappy to be your target to learn how to gap fill? I didn't quite understand that.
Yeah, that's okay. Thanks, Chris, for the question. In fact, this is what we call self-supervised learning in AI strategies. So basically, we learn directly on the observation. So you're right, the product is gappy. So what we do, we remove again additional observation from the SLSTR product. And this observation we removed, we keep it for training the neural network. So it will train the model on location it doesn't know as inputs because it's not used and it's removed from scratch. And of course, you have gaps in the end, in the inputs, but you hope that what you learn on this data that you removed, you will be able to generalize everywhere. It's not the same data, of course, but you're learning an algorithm to fill in the gaps based on, as any algorithm, the neighbors around in space and time. And doing that, you hope that you learn something that is very general. And in fact, it works. It works in terms of validation for the North Sea Baltic Sea that I presented last year. And we are right now running validation to see how it performs compared to the optimal interpolation used at DMI. And we are quite confident that it should be the same than last year with significant improvements.
Sorry, if I may, Maxime.
Yeah.
I didn't understand if you validated your output with in situ data.
We did it last year on the North Sea Baltic Sea. Basically, it showed similar performance than the optimal interpolation. And for independent satellites in the previous experiment on the North Sea Baltic Sea, the AI model was performing better. So all in all, I think the AI strategy is behaving a bit better than the optimal interpolation. And again, why? Probably because this family of algorithms are more prone to escape from the optimal Gaussianity and linear assumptions that are used in traditional data assimilation algorithms. Here, you're really training your algorithm on what you want to reconstruct, meaning your observation, even if they are a bit noisy, but at least you're closer to the real assumptions behind your dynamical system. You do not introduce any Gaussian or linear assumption as in most of data assimilation algorithms. So just for that, yes, we validate on in situ, but the model is not trained on in situ. So that's why sometimes I guess the performance is just as good as data assimilation and does not perform better. An AI model is always trained on something and trained to do something. And right now, the algorithm is trained to be optimized on satellite observations, not on in situ.
Okay,
it could
thank
be
you.
in the future, I guess.
Thank you. Chris.
Okay, thank you, Maxime, for the presentation. I have another question regarding the validation or if the improvement of this methodology with respect to the analyze level 4, the other L4 product, with regard to the effective spatial resolution and the dynamic properties of your output. Have you looked into that?
We are right now doing it for the global SST product. I can give you some feedback. For the North Sea Baltic Sea, there was a very strong improvement in terms of effective resolutions reached by this kind of product and this multi-resolution strategy. The paper has been published last year, so you can see the results in this paper. In terms of spectral metrics, you see a very big improvements. And just looking at the maps, you can see that you really retrieve a higher resolution than with traditional OI or data assimilation algorithms that tends to smooth out a little bit too much the observations. Yeah, and we plan to do that as well on the global product right now.
Okay, thank you. There is a question over there for Daniele first. Okay.
Thanks a lot, Maxime. I may have missed it during your presentation, but I was wondering if the loss function you employ for the training contains any physics-informed constraint, and if not, if you are planning to introduce some and how. Thanks a lot.
Yeah. I think the algorithm we developed a few years back in time on SSH is very generic. So right now we are not using any physical information in the model because it's trained only on observations, but it can be, meaning that since it's backbone on a data simulation framework, it would be very easy to plug in some physical information in the prior term I showed during the presentation, because we learn both a prior and an optimizer. And the optimizer is something on the side, but the prior term right now, we could embed any physical information we would like into. So this is something that, yeah, we would like to investigate in the future.
Thanks.
Okay, thanks. Yes, we have another question.
Max, how you are taking care of the dynamical consistencies between various parameters? Like, for example, SST is also correlated with currents and the salinity sometimes. So normally in traditional data assimilation procedures, the increments are affecting each of those variables so that the system remains dynamically consistent. So how you are taking care of that?
Right now it's not done, but again, it can be in future work, simply by considering first the model in a multivariate setup. I showed something focusing on pure SST-IST observation, but we could embed additional satellite information on all the variables related to SST. We are right now doing it not with SSS, but with SSH, for instance, which can obviously help in relaying the information in terms of currents between SST and SSH. So this can be done, and this is done right now with another internship at DMI and EMT Atlantic in France. And regarding, yeah, the dynamical consistency, I guess it's a bit of follow-up of the previous question. For now, there is no physical information embedded in the framework, but it can be, and it already has been done in some derived experiments of this setup, where basically when you train an AI model, you have a training loss, and you can add regularizers to help retrieving some physics. And we can imagine to add some additional constraints in this training loss to satisfy that the current, for instance, are physically consistent in your output. So it's possible, it's just additional work. It's very plug and play, this kind of approach, but you have to improve it by improving the training loss with physical constraints, or the architecture of your AI model, again, with physical constraints. You have the two choices on the side.
Thank you so much.
Okay, thank you, Maxime. Are there other questions also for the other speakers, if you want? Yeah. Okay. I would like to ask a question to Lucas, if it's okay. I was wondering if you are planning to assess the effective resolution of your data, maybe via spectral analysis or something like that, to see if your processing is actually, reflecting the 2 kilometers nominal resolution?
Compare with what, sorry?
If you were trying to do some spectral analysis or assessing the effective spatial resolution, maybe analyzing.
Yeah, in fact, we are waiting to have the daily product to do more like cases, study cases in different areas. We already have some institute data that we can compare in some areas like Rio de la Plata. So we are waiting that to do the comparison.
Yeah, that makes sense. Thanks. Okay, so if there are no other questions, let's thank the speakers again. And we move on to the discussion on Greece priorities on this topic. Any ideas? Ed, do you have some ideas since you're talking? Anything? Is artificial intelligence a priority for Greece people?
Yeah, so my concern is, or prior to, I think we need to think about is like GRIS from the data distribution and data production is becoming a little bifurcated. We have distribution nodes all over the world now, data production sites in Europe and Japan. We heard a large user base in India now. And I think we need to think a little carefully how we harmonize that. Of course, we have the specification that's in NetCDF, but then how about the access, right? How are users supposed to kind of know and access? So there's kind of like a discovery part of that. And perhaps this VDS technology could play like a positive role in ameliorating some of the access problems, at least, I think. And yeah, so I would encourage people to look at what we've done. We've carefully documented in recipes that people can use really out of the box to create these. And they can contribute to the community. It's an open source development community that we really want to build. And as our data products get more and more complex too, this technology, especially IceChunk, is very adaptable. And we can still produce individual NetCDF files and virtualize them. So the actual VDS is very lightweight and overhead, but really the access and speed capabilities of this data, really where it resides is almost a little agnostic, as long as you can get to it by an HTTP link or an S3 link in a cloud. It's really kind of like a very agnostic technology. So anyway, I'm just throwing that out there, something to think about.
Thank you, Ed. Yes, Chris.
Okay, if anyone is, yes, I will try to break the ice. So for me, as my personal view on that, and after seeing the presentation in this session, the main concern or my question is to which extent AI is providing data or outputs that are meaningful from the physical point of view or dynamical point of view. Of course, and that's why I made that question. And yes, you can see from a visual inspection that you may have more structure, but is this meaningful in the sense, because I mean it can create whatever. So what I'm trying to say is that we need to find metrics as the one that we proposed in the future fidelity task a few years ago, and that I now was referring. For me, that thing, and it's in the line as the I don't remember his name, the Indian colleague there. over there. You were saying to compare SST and salinity and current with results, but the point is that, and they should give you same information, but it's not always related directly SST to the current. It should be, but not always it's the case. So it's that's my point. So what I'm trying to say is that for me, what we need is to assess if it's giving meaningful information. That's my point.
Yeah, I have a follow-up comment that we all know AIs tend to remember or memorize the common and the regular variations. So they are very lack the ability to track the extreme things, even because that many of them that never happened before. So I think after these talks in this session, I think no one has never showed how the data probability density or distribution changed before they added the AI predict or generalize or even interpolated data. So how will the directly observed SSTs behave and how the AI generated behave? We don't know. So I think you should at least check the distribution to find whether they are regularly behave or just maybe in the center of the distribution and lack the extremes. Yeah, that's what I want to comment on.
Thanks. Anyone else? Yes, Pallavi. I think there is a micro over. Yeah, okay. I think it's off.
Yeah. So for Ed, so every year, if we look last 3-4 years, every year we are talking about some new technology, which is how we can make this data better and how we can put them on cloud and all those things. It's good we are doing it, but then we have our users, they are not technically advanced, they just want Excel sheet, or they are not even able to use the netseria file. So how do we get these two worlds together? So if we can use AI to help both sides, like something simplified, data automatically getting readily available for users, or how we get these two worlds together.
Are you expecting me to answer? You're right.
And maybe Ed.
Can you?
Yeah, maybe this is a new action for the GRIS project office, because before you took over, there was actually a training course being developed. And part of that was on accessibility and working with the GRIS data and applying and learning about all these new technologies. And so, yeah, we have this great cookbook chapter again. We could develop a modest training course on this VDS stuff quite easily, I think. Something for an hour, 60 minutes or something for the global audience. So, I mean, we're in this business. We know there's always new technology out there and always new and better things. We're scientists looking at the cutting edge and stuff. So how to bring new users on board? I mean, there has to be, I think, from the GRIS science team, more like maybe more kind of outreach in your national communities and your agencies and stuff to start using these data and showing them how to use the latest data products and the limitations and the caveats of every product that you know about, I think are important too. So I think there's some personal responsibility that goes on there too.
Okay.
I think that's a fair comment from Ed, but maybe we need to think quite carefully about Pallavi's comment about at what level we pitch the training, because I think she is right that some users want to come along and get a CSV file, and it has to be really, really easy. And so there's a range of targets we need to pitch, and there will be people that would like to have something simple, like they want to follow a ship and they want our data, you know, day by day following a ship track. And probably your technologies do enable that sort of thing from an enormous data set, but then they will only actually use the Excel file at the end. So we got that extra bit beyond just getting the data down in Python that we might need to think harder about. But I had a question for you as well. If we wait till the end of the summer and we get this HTTPS version of, I think it was ICE chunk, all sorted, and that looks like it's a really useful way, is that then going to be something we can use for 5 years, or is it going to be stable, or is it going to keep being a moving goalpost for us?
Well, yeah, that's a good question, Chris. I mean, you know, technology always advances, and you always, you know, try to keep up. But it looks like Ice Chunk, you know, it is also, you know, it's been out there for a couple of years, so it's mature, but it still has these little hiccups. It works very, very well in the cloud, but it has some hiccups when you try to access it outside the cloud, and that's the part they're going to solve. And you know, Earth Mover is this company behind it is a very dynamic company and wants to work with you know, people that are in the leading edge and pushing things forward. And I think that's where we want to be too. So perhaps we don't produce, you know, we produce ice chunks with, you know, the most mature library, and we kind of freeze it there for a couple of years or something like that. But, you know, the technology does advance, and, you know, there's no guarantee that something better than ice chunk or, you know, ZAR or something will be invented. The nice thing about these virtual technologies is our mode of business of creating things file by file. It plays very well with that model, right? There's no extra overhead on the data archive to implement these technologies. Very lightweight. It doesn't cost you any storage. You just have to have like an S3 bucket where you put the actual VDS. And so from that perspective, it's very easy to maintain. And Ice Chunk will give us the great benefit for those data producers that do want to you know, make this technology public, is that the appending part of new data, like near real-time data that comes, is very easy to append. It's like a database, and there's actually version control where you can have like multiple versions in the same Ice Chunk store. So I could see you could have like a deprecated version and a new version, and you can access them the same way. So it doesn't really answer, I'm sorry, I don't give you the best answer to your question. But yeah, I think, you know, things like Ice Chunk is something we do want to move forward, because NASA is looking at very, very carefully at an enterprise level. That was kind of my last comment. A lot of things in flux, but they see this as a technology going forward. Thank you.
Jorge? I just wanted to just quickly add, because of also the focus that we've had on high latitudes and regional high resolution data sets. NASA has 2 field campaigns that I think would be very, very useful also for validation and calibration purposes. One is the SASE campaign. All of this data is on the PODAC website. And the other one is what we call the Submesoscale Ocean Dynamics Experiment, S-Mode, which is off of California. I can't think of another field campaign like S-Mode that provides the both the validations for gradients as well as high resolution too, and close to the coast. So you have the issues of dealing with also the land masking and data sets, especially with salinity. So anyway, I just wanted to throw that out. All of those data sets are also on the NASA PODAC site. Thank you.
Thank you, Jorge. Anyone else? Also online, if you want to contribute to the discussion. It's very early for them, I think. Okay, then thank you very much to all. It's coffee time, I suppose. So we came back at, not sure, 3:45.
Okay, so we will start this this session about the next GDS version, so version 3. So for those who are not really aware of this RGTS task team, just a reminder of what we do. So we are working on the specification of the GHRSST system, so interface and architecture, and that includes the format specification of GHRSST datasets. We help also to define the roles and interaction between the GHRSST entities, the minimum services and interface that they should implement to serve the GHRSST data, and to ensure that the overall GHRSST system operates according to this specification. And we also support these entities to implement these services. So don't hesitate also to contact us, me and Ed, if you have issues with this. So the GHRSST data specification is one of the great achievements of GHRSST. So it provides a common format for all GHRSST dataset, and it's been used by many agencies and for more than 150 datasets and many more coming every year. So this is the key aspect to maintain the interoperability between the GHRSST datasets and services. And just to remind you that the latest version was published last year, so this is GTS 2.2. It's available as a Jupyter book, and it's very close to the previous version 2.1. So the objective of this session is to review the different propositions for the different issues that were open on the GDS GitHub repository with respect to the future of this GDS. So we have been exchanging through this GitHub issue tracker in the last year, and we have also already had session in the last 2 previous GRIS meeting. So now it's time to wrap up this and to draft this version 3. So we will recap here the different issues and propositions that we suggest, and if no disagreement or concern is expressed, this proposition will be considered as adopted after this session, and we will work in the coming months on the actual draft of the version 3, which should be issued by fall this year. So for some aspects, there may be some other evolution in future because maybe some of them are not mature enough right now. So there may be some refinement of the requirements that can be added later. But the main rule is that they should not break the backward compatibility with the baseline of the GDS version 3. So we may add new variables, new attributes, stuff like that, but not change what will be in this first baseline. So also this GDS 3, when it will be available, it doesn't mean that you have to change your existing data sets. They can run on with existing format, but that should be the reference version for any new data set that will come after. So we'll review now the different issues and propositions that we have. So one of them was the product string of GRIST datasets. There was some confusion in the current specification between the GRIST unique identifier, the product string that is used in this identifier, and the file name, which was using another kind of product identifier. So we want to simplify this. We having one unique product identifier that will be used also in the file name. Also, an issue that we had with this identifier is that, especially for level 2 and level 3 uncollated or collated data set, you should provide the name of the mission and instrument. So we were referring to COS as a reference for selecting this name, but for identifier like this, it's really a pain because of many characters like hyphens, underscores, or even spaces, and also because the names can be quite long. So in the new formulation for the GRIST product identifiers that we propose, which apply mainly for the level 2 to level 3, we propose to replace the COS mission and instrument name with a shorter ID, so without any of these problematic characters. And this list of short name will be maintained in a table, in a dynamic table, in order to ensure that everybody use the same. So you have on the right side here some examples of the kind of short strings that we could use for instrument and mission. So this is an example of how this new product strings will look like. So it's not much different from the previous one, except that it has been a bit simplified for the level 2 to level 3. For level 3S and level 4, there is no change with respect to the previous rule. So since we are changing this product identifier, we are also changing the file naming, which was using a different combination of fields. So we have simplified this file naming by using the new product identifier that I showed just before. And also there was an issue with the SST type field that was in this file name, because we put this information previously as a field in the file name. So there was this SST FND for foundation, skin, subskin, and so on. So it was starting to be a bit messy, especially with data sets that are providing different SST or even IST. So our proposition here is to completely remove this field from the file name to avoid any ambiguity on the. Then there was a question on how should we change the reference format for GRIST products. So far, we have been relying on netcdf4, but there are new formats that have been around in the last year, like COG, ZAR, and so on. Yeah.
I just wanted to clarify how the session's working. Are you, if you've gone off the slide, have we by de facto accepted it, or are we talking about them as we go? How do you want it to work?
Good question. I think it would be better if we interrupt at
Yes.
after each slide.
After each slide, yes. So if anyone has any interruptions on any of those, we should have them now and then go on. Yeah. Great. Thanks.
Hi, Jeff. Can you hear me? Sorry, Gary, online.
We can hear you.
Okay, yeah. Just regard to the file name, is there any reason the additional segregator is removed, or is that something that can still be considered? Because it's quite useful if you've got different timeliness or etc. to include additional information.
I'm sorry, I did not understand what you, can you repeat?
So in your example at the bottom, you don't have the additional segregator. So is that still included, or have I just missed that?
Which segregator?
So in the file name, you have the additional segregator before the.
Yes.
Is it? But you don't have that in your example. So is that to be removed, or is it still to be included?
Yes, this is no. It has been removed because it's part of the GHRSST of the new GHRSST identifier.
Okay. So anything that we would provisionally include in the additional segregator, we now have to include in the ID.
So in this example, for instance, the globe in the Ostia file name, this is the segregator has been moved to the identifier.
Okay, thanks.
Okay, so back to the format. So then after discussing this, so we did not find any critical advantage to switch to.
There's another question in the where Igor is raising his hand. So go ahead, Igor.
Yeah. Hello. So I have another question for removing SST type. So does it mean that now we don't have, if I look just at the Ostia NC file, we don't have any information basically what is inside apart from looking at the sum identifier? Before we had, we have SST type, we knew we could add ST type, and have surface temperature only, and that's what we did for the eye surface temperature. But in this case, we are completely removing information for any external users, what is the content of the file.
Yes.
Or is it foreseen? Because even if we combine many variables, I think we can still keep like ST as a surface temperature. And I think that's how we are going in the future.
Yeah. I don't know, it's an open question, but I think it will, it makes things confusing, and it will be even more confusing when we have maybe later this ultra high resolution SST product where you may have also land temperature inside or others. So, and anyway, if you feel it is really necessary, you still have this additional segregator where you can put what you want, in fact.
Okay.
No.
So excluding that SST type is optional. It is not compulsory. That's what you are saying.
No, yeah, it's removed, but you can add it if you want to keep it. You can add it as a segregator in the product identifier.
Yeah. So that means I can keep that SST type in the file name, and still my file will be GDS3 compliant.
Okay.
Is that going to be okay?
No, because anyway, in the GDS3, there will be some breaking changes, so none of the current dataset will be compatible with.
Yeah, because at the Bureau, we saw data from 1992. We have large number of files, and
yes,
yeah, we will have to reprocess like.
No. As I said before, existing dataset, you don't have to change anything. You can continue as they go. This GDS-v3 will only apply to new dataset.
So totally newly developed data. Okay.
Yeah.
Not the existing data set.
Yes.
Okay, then.
Yes.
That makes life easier. Sorry, thank you.
Just a question on the automatic reading of the file names, if the parsability. Does the additional segregator have any rules, for example, restricting rules of hyphens within it so that we can always know by counting the hyphens which bit we're looking at or something like this? Because that doesn't seem to be reflected here.
If you really want to put any character in additional segregator, then for automatic decoding, you will need to cut with these hyphens and isolate. You have to cut from the beginning and from the end to have the remaining segregator. So you cannot you cannot automatically decode the full string based only on this hyphen character. So you can do for each field, but the GHRSST are not. So you can cut out the date, the time, the file version, and so on. So it can be in an automated way because there is not that will go into that. But then you are left with this GHRSST identifier. So this is the way you should decode it.
And is there any restriction on the length of the characters of each field?
No, there is. We didn't have any so far, so
Okay.
we do not change that.
So the way of decodifying that would be the separator of the slash?
Yes.
I mean, slash, no, I don't know how to spell it. Okay.
Yeah.
Yeah, so that would be, and the additional aggregator is just before after the GHRSST. Yeah, that's it, no?
Yes. So the segregator has been moved here in the product identifier.
And I have another question. I don't know if it might be confusing for the users if we keep the old nomenclature for the file name as it is, and it just apply for the new ones. I don't know if it would be confusing. That's something I.
Yes, but it's a trade-off. In the current version, it was very confusing between the different identifiers that were being used. And we can see that sometimes also in the catalog because it was not always a proper identifier. Sometimes it was taken from the file name, sometimes from this identifier. So this is a clarification of the rule. And for that, we need to address the conflict that were existing in the version 2.
I have a comment for this SSD type. So the basically that I don't want to change the file convention name if there is any other way to keep it. So I'm wondering why we can add the other category like IST or ISST in this SSD type. And so keep the current version and to make a place to additional the SSD was ice surface temperature can be included in this file naming.
The problem is that now many datasets they provide different SST, so you may have the skins, the depths, and so on. So we may end up with a large number of possible combinations. So we didn't find a way to address that through a simple short keyword. But if someone has some suggestion, it's something.
Sorry, I cannot understand what you answered. Sorry.
I guess what he's meaning, but I don't know any product like that, is that it might be the case that now or from now on, some files will contain different variables. So they will mix in, I don't know, correct me if I'm wrong, but I understood that in the same file, you could find the SST skin and foundation in the same file.
Yes. No, skin or depth. Some you have some data set, you have skin or depth. Some,
Skin for foundation would be level 4 and the other thing would be level 3. Okay, I don't know.
I may not understand that why is that we cannot keep the type of the things and with the addition of the other the category type of the SSD. That the reason to remove this one, but yeah, maybe that I think that there is other things to be discussed. So just I make a comment. Yeah, thank you.
Okay, so back to the format issue. So we decided eventually that there was no critical advantage to switch from NetCDF4 to ZAR or any other formats for now. So especially also with what Ed showed before with some way to optimize the NetCDF4 over the cloud and apply this virtual ZAR metadata and so on. So we can emulate anyway ZAR with NetCDF4. So we propose to keep the NetCDF4 as the base format for a GRIS product. But at the same time, we acknowledge the fact that for some reason, people may convert GRIS data to other formats for some specific services like all this ARCO analysis ready format or COG for visualization and so on. So what we plan to do in this new GDS version is to provide rules on how you should convert NetCDF4 to these other formats while keeping the core information and metadata that are really important in the full NetCDF dataset. So then there was also a question about using NetCDF4 groups. It could have been interested in particular again because now in some data sets you can find different SST variables who could come with their own quality level, uncertainties and so on. There may be also different views on an instrument, so there may be a need to separate these different views into different groups. Another case was possibly also multi-resolution level 3S, where you would have you would separate the microwave data who have a coarser resolution from geostationary and polar orbiting infrared data. But that will probably bring a lot of heterogeneity in the GRIS dataset. Also, some of the people who discussed this issue were thinking that maybe GDS, the groups usage of groups was quite complex and unnecessary at this stage. So the proposition for this is to keep as it is now and not using NetCDF groups. So in the case where we have like a multi-resolution S3S, for instance, that should be handled through 3 or 4 different collections with their own dimensions and SST variables. It may be possible to add additional SST variables and associated ancillary variable, and that should be handled through suffixes instead of groups. You are? Okay. Okay, another point, data types, scaling and quantization. So in the current GDS, so we are using for several variables, scale factor and add offsets. It has been a source of problems. Some users don't use them as they should because they hard code instead of dynamically reading these values. So if they are changed somehow, the unscaled values are not realistic anymore. Plus, there are also some clipping issues for values that were beyond the range of the possible values of for a given integer. And also now with modern readers like Python, Xarray, all the data are unpacked seamlessly. So we were questioning if we should keep keeping these attributes and store floating values as a floats and never convert them to integer. So the consensus was that we should follow the CF convention. So we should not forbid the use of this offset and scale factor attribute for the reason but for the reason I explained before, it is not recommended. So it's preferable to use when you have a float value to keep it in a floating types. So there are other ways to compress floats than explicitly packing the data through add offset and scale factors. So one of them is quantization using the number of significant digits. So it is an option in the NetCDF API, and it greatly also compress the size of your variable arrays. So our plan is to provide recommendations on how to use properly these quantization arguments. And also we allow more flexibility on the data types. For instance, even for integers, if it does not fit on a byte, you are allowed to use a 16-bit integer or more. So there is no constraint anymore on this, since it's seamless anyway when you read the data. Okay, then following Ed's work, so we will provide in the GDS some recommendation on how to properly optimize the NetCDF format for your dataset. So with respect to the chunking, the storage of the metadata, and so on, to optimize cloud access and subsetting. So I think you have some slides about this.
Please use the micro. Right. Is there?
Yes. What did I do?
Okay. Okay, hey, so I'm going to talk a little bit more about cloud optimization strategies, and they really fall into two buckets. One of them is the chunking that I alluded to with the VDS presentation, consistent chunking, and the other part is optimizing the internal metadata of the H5 for the H5 data model. So NetCDF4 is H5, right? So I'll be talking about H5 a lot, but this is all germane to the NetCDF4 data model as well. And the internal metadata, just FYI, the internal metadata I'm talking about is not the global attributes or the variable level metadata. It's actually it's part of the HDF data model. There is metadata that tells the NetCDF or the H5 API where to find stuff inside the file. Okay, so I've talked about the two unique approaches for optimization I want to tackle, chunks and H5 metadata optimization. Just a little bit of background. These actually, it's not my work, right? I got a lot of this stuff from Alex Jelinek at the HDF group. who just kind of mentored me, informed me about a lot of these things. A lot of these things I learned at going to conferences like the Fall AGU and the ESIP. So this is not my work, or not largely my work. There's other people out there. So I'm going to be leveraging things I found from another good website called Cloud Native Geo as a group. They have a best practices website for cloud optimization, not just on these topics, but they talk about COGS and all that stuff too. And I'm also part of the Part 4 NASA interoperability best practices that hasn't been published yet, but I've leveraged some material from that. And again, this is stuff I've been learning at ESIP and AGU and from the HDF group and Development Seed. And and these some of these practices have actually been implemented on a real NASA Earth mission. The NISAR mission has implemented these practices, and probably some other missions and initiatives I don't know about. Okay, so the first thing I'm going to talk about is the chunking. Of course, when you implement chunking, you reduce the overhead because you're just getting the pieces of the file you need to support like regional use cases. Everything works better if the things are chunked, if the data is chunked properly. Like subsetting APIs work faster. This lazy loading idea using Xarray works better, and the chunks can be individually compressed, and these chunks can be accessed both in and out of the cloud. Both spatial and temporal dimensional time chunking can be done. They really kind of support different use cases and file structures, but because the GRIS files are just one time step, maybe in some cases there's two, we look at the spatial chunking. And I'm sorry I don't have a figure there, but think of the chunk as like a data rod, a single spatial chunks that an API can quickly access across an entire collection of files. So like there's a small region of interest, and you've chunked it as like 100 by 100 pixels, and you just want to grab that across the entire $20,000, 15,000 file count for something like Ostia. So yeah, we want to optimize the spatial chunking in the spatial domain. Okay, so how big are these chunk sizes? And it's really kind of like no one size fits all, right? If your chunk size is too small, like in the order of the kilobytes, you're going to incur too much file I/O and stuff when you want to start accessing these data products. And if it's too big, it really kind of defeats the purpose of having a chunk. In fact, there are some GRIS data files that the whole file is just one chunk, right? So kind of defeats the purpose. And what the chunk size also, of course, depends on the file size itself, right? How big it is. So where's the sweet spot? This is all stuff you need to kind of think about the user access, how the user is accessing, and how where the data is located. And if it's in the cloud, like the NASA Earth data, there's an optimized range for HTTPS read requests in the 8 to 16 megabyte range. Of course, the chunk needs to be kind of all even and consistent for a lot of these technologies like Kerchunk and IceChunk to work. And the chunk size should also be on the order of the H5 metadata consolidation size. So I'm going to talk a little bit about that in the next section. But all this really indicates for the data products that we provide at their size, that something on the order of 1 to 16 megabyte chunks would be good. But I have seen examples, or other examples out there of very large model data sets that are like 100 megabytes chunks, and they also report good performance. NISAR has chosen 4 megabyte chunks for their data products. I might be off by a factor of 2 on that. Maybe it's a 2, but it's in the small megabyte range. Okay, that's chunking. I'm going to talk about this esoteric topic about okay, here's a little statement from the Part 4 interoperability recommendations for chunk sizes. They should be the same size and consistent, right, for things to work good. So they must ensure the chunk shape fits perfectly as tiles across the entire variable domain without having any edges or partially filled chunks. Things can still work, but they don't work as well. So it's not desirable to have uneven chunks. And we actually have a little simple mathematical relationship for data producers to be able to calculate that for their dimensions, their dimension sizes. Those interoperability recommendations are going to be published probably the end of this summer or something like that in a few months. Okay, so now this esoteric topic of the metadata optimization and why H5 in the cloud is slow, right? Because in the H5 metadata model, the way when you default write a data set or a data set is H5 variable speak for a variable, a netcdf variable. When you write a variable, you write a file, these metadata blocks that contain all the information about how an API can read and go fetch data are small, they're 4K, and they're kind of randomly distributed all over the file. So when you make a request to go fetch some data from a H5 or netcdf file, it has to traverse that file until it finds that metadata block that tells it where the data is. And that could be the first metadata block it reads, or it could be the last one. And so when you're working locally, this all works very fast because you have very fast read IO access to something that's stored on your local computer. But when you're in the cloud, you're doing all these HTTP requests to find and retrieve these metadata blocks, and that's what slows it down. So if you could aggregate all those little metadata blocks, that's in the yellow, the raw data chunks are in the green. If you could aggregate those and get everything in one read, and then you know exactly where to go in the file to get the information that you want. So that is the philosophy behind this H5 netcdf metadata optimization. And this is something that the NISAR mission has implemented. Okay, yeah, so here I just kind of reiterating what I just described. It's called, the name of this this aggregation is called paged aggregation. And this is actually a feature that has been built into the H5 library since the get-go, way back when they designed H5, but nobody never really appreciated it or used it because they didn't really need to. We were all still working with files locally and stuff, but now we have this problem where it's in the cloud. And so if you do implement this page aggregation, you can actually consolidate the internal metadata in separate file pages. So they're kind of like the super block that contains all the metadata. You might have 1 or 2 file pages, but it's recommended to be this 4, 8, or 16 megabytes. And really, you need to stop thinking about megabytes when you're in this world and this new term, maybe bytes, because you need to write exactly those number of bytes, right? So it's, this speak is maybe bytes. You don't talk about megabyte, factor of 2 versus the factor of 10, right? So you need to write it as 4 maybe bytes. All right, and the selected size should be a compromise between the, here's the relationship, is the selected size between chunking should be a compromise between the typical total file internal size and the metadata chunking. And to optimize performance, the chunk sizes should ideally align with the page size or be a multiple of 2 thereof. Now it says it should not be bigger than the page size, and that's actually what's in the interoperability recommendation. I'm not sure if that's exactly true. It should be about the same size, smaller, the chunk size, smaller than the page size, or maybe a little bit bigger. Because when you're actually executing and reading information using the H5 API or netcdf API, it's actually reading things in those file pages size. So if your chunking is much, much smaller or much, much bigger, it kind of defeats some of the purposes of doing the chunking. So that's why the chunk sizes should ideally align with these page sizes or be a multiple of 2 thereof. Okay, here's a little code snippet how this is really, for the data producer, it's really straightforward to implement this. This is, if you wanted to do this for netcdf, right, this is what you would use, the H5 netcdf package, and set your page size there in bytes. So it's 8 maybe bytes is what we're going to be writing there, 8 times 1024 times 1024. And then there's some arguments when you actually open up the and start to write to an H5 file. You just pass it some arguments. You call it that fs_strategy page, and you just set it the number of bytes that you want. In this case, there are 8 maybe bytes. And then you write it, and you're done. And that, in a nutshell, is the optimization of the NetCDF for cloud access. I think that's my last slide. Oh no. Okay, yeah. So at the cloud optimized geospatial formats, they have a nice little checklist. I think that we should take a look at, right? And check, right? You know, the format supports consolidated metadata chunking compression. Yeah, NetCDF4 do. Check. The metadata has been consolidated. It's talked about that chunk size are not too big or too small. Appropriate compression algorithm has applied. There may be some things we need to be cautious about with the chunking or the compression algorithm that we apply. Yeah, the expected use case for the data were considered when designing the chunk size and shape. And the last one is about reading from cloud storage. I think that's my last slide. And the other one was on ARD stuff. Maybe we just stop right there. So any comments or just march along?
It sounds like to me that in summary, it's easy to do if you follow someone who's thought it through already. But is it easy to check whether someone has got it right, and will there be a checker for the optimizations?
Yeah, that's a good point. We didn't really think about that. Well, yeah, we could design some kind of checker for the data producer and stuff. We should probably have like some simple like examples of performance tests and stuff like that. I mean, the performance tests already exist. I mean, I have some. I've done this on the mirror, applied this technique on the mirror, and seen some modest improvements in cloud access. And you know, the bigger and more complicated your product is, the better this technique. I mean, there's all kinds of the NISAR group has all kinds of performance metrics, and some of them are quite staggering, right? And we're talking maybe 2 orders of magnitude faster access in the cloud. So something that takes, you want to read a couple pixels, it takes like 150 seconds. Now you're like a second or less. So there is some astounding examples of performance increases. But yeah, we should think about something for the producer to make sure that they're doing it right, that they get the right chunk sizes, the right file pages, stuff like that.
So Igor, do you want to say something?
Yes, thanks. So thanks, Ed. Quite interesting talk. One point first for the library of NetCDF, because I think last year you mentioned that this metadata was not yet implemented in some of the NetCDF library. Is it now implemented correctly?
No, still not, and I don't know if it will be. That's a good question. This example that I just showed, use the H5 NetCDF packet, Python package, which is the NetCDF bindings to the H5 Pi package and stuff. So as far as I know, okay, this is the most elegant way to do this. There is a way to use the H5 libraries to write a valid NetCDF4, but it's quite not complicated, but you got to be careful what you're doing, right?
Yeah.
So there is another pathway through just using H5 libraries, but I think probably a little bit too complex for most data producers. I think for right now, this is the best way forward to implementing cloud optimization for writing out NetCDF.
Okay, thanks. And maybe just to comment on Chris' point, as you know, we have a GDS checker, so I think that's the best way actually to include if the optimization is already inside the product. So I think we can take it on board and try to do it for the next versions. But again, we need to have full libraries available and everything to be ready for this. Thanks.
Yeah, I think there are ways to include that in the checker. So we will look at this. No more question.
So there is also a question from Christina. So go ahead.
Yes, could you hear me?
Yes, we can.
Okay. I only want to clarify one point. I mean, if I have to deliver my file, I mean, from Copernicus to GRIST, the format that GRIST will accept still is an SCDF format, or I can put file in other format like a ZAR format. As in Copernicus, we are discussing the kind of file we have to put in a Copernicus catalog. So I'm wondering if the NetCDF file, the NetCDF format is still the only format that GRIST accept to become a GRIST file, or a file delivered by GRIST catalog.
Yes, so for now, for now in Copernicus, this is still a NetCDF4 format as a baseline format. So
now, but I think that they are discussing about changing this rule. So I was wondering what will be the direction, and if the direction can remain the same between GRIST catalog and the Copernicus catalog. Sorry.
did not catch the last part. I'm not sure I catch the last part of what you what you said.
I mean, if I have to, as I have to share or to deliver the Copernicus file from Copernicus catalog to GRIST catalog, is the NetCDF file format the only one that GRIST will accept now and in the future?
I don't see the link between the format and the catalog. But in any case, for your concern about the format, so the GS3 version format is compatible with the requirement so far from Copernicus.
Okay, thank you.
Okay, so maybe we move on to... I don't know how you... Okay. Okay, so back to the other issues. So another one is the time coordinates. So as you remember, so far for level 2, the time was split in two variables. So a one-dimensional time variable and SST DTAM variable that was two-dimensional. So yeah, it created all sorts of problems. And also there was this time dimension in the L2P. So in fact, all L2P variables were three-dimensional, whereas in fact they were physically two-dimensional, and there was no use for this extra time dimension. So we propose to remove this time dimension from level 2P variables. And we also propose to replace this combination of time and SSTD time by a single time variable, which can be two-dimensional if you want to give a time to every pixel, or which can be also one-dimensional along track. So if additional SST variable are added with a different reference time, they should be named as it is stated here, so time off and the name of this additional variable. So for level 3, the time variable and the time dimension remains. So all variable remain three-dimensional. So this allows the temporal aggregation of all these grids to provide like a three-dimensional data cubes. In level 3S, SST DTIME is replaced with OR time in order to align with original latitude and longitude. But now it will be a time value, so it's not anymore an offset. And again, if additional SST variables are added, then you should it should be named like in the following. For level 4, the rules in GDS v2 still applies. There is no change because it was a one-dimensional time variable. So for spatial coordinates, so we need to better describe the projection for gridded data sets. So for instance, with CF compliant CRS variable, we should keep also mandatory lat long variables in level 2P, but I will come back also about this a bit later. Especially, there was a question on whereas we should keep this two-dimensional lat long variable, which take a lot of space. And in fact, in the CF convention, there are specifications to compress the lat long. So using this type point grid, and over which you do interpolation to get the intermediate lat long. So these were all the issues that we looked at. So we came with different propositions. So the first one is for level 3 and level dataset to add the CF boundary variable. So this gives the limits of the actual pixel size. So the boundaries of the pixel. So this does not apply yet for source data. There is no equivalent. So this is to better reference what the latitude longitude coordinates refer to. Is it the pixel center and so on? So at least for level 3, level 4, you can provide this limit thanks to this CF boundary variable. So then we recommend to add the CRS variable and the corresponding grid mapping attribute for every variables, even for isolatitude and isolongitude grids. Then there are issues related to the geolocation error and the compression of lat long, and this will be addressed in the ultra high resolution SST task team. So I will come back on this later. So then there was the how to properly handle ice surface temperature and sea surface temperature. So there was some discussion about this in particular in the high latitude task team. And so the proposition here is led by Gary. So I will let him go through this.
Okay, thanks, Jeff. Yeah, so the proposal here is how we introduce IST, or in our particular interest in GRIST, the IST being sea ice surface temperature, into GRIST data sets and into the GDS. So this is just a summary. There is a more detailed talk, which is available on the Moodle should you have any other questions or things we don't go through now. So the proposition is to add a high-level retrieval categories. So this could be SST, IST, LST, or a mixed. It could be a combination for a particular pixel to the GDS. So this is above the current GRIST definitions. And then to immediately look the IST for GRIST in this particular case, we're going to refer to sea ice surface temperature. That's our specific interest. And then in products where the data would include more than one category, then you would use the generic surface temperature instead of specifically having sea surface temperature, etc. And this allows it to be used for any of those combinations. And we would use LTP flags to indicate which categories are applicable for individual pixels. We already, for example, have ice flag. We already have a land flag. So this should be, again, very straightforward to do. For level 2 and level 3, at least at L3C, which is a single sensor, the IST update should be fairly straightforward. At the moment for L3S and level 4, it's not clear as to what, when you start to merge different surface temperatures at different depths, what this actually means. So we need a little bit more time to work with the experts on this. One thing that will require, though, is to deal with passive microwave observations. So we propose to introduce a new CF standard name based on the radiometric depth. So we would introduce surface subskin temperature for passive microwave IST retrievals. Now, obviously, over ice, this is not the same depth as it would be for the infrared sensors. But of course, this is true over the SST domain anyway, and this is why the GRIS definitions are used on the radiometric depth. So we hope that's not a controversial issue, but it may require some further discussions later. Then in the actual product itself, we propose at least a level 2 to have a single surface temperature field, and you would use the flags to determine whether it's uniquely SST, for example, or IST, or if the producer has included a mixture. And there are options using cell methods attributes in level 3, should you want to include IST and SST at level 3 separately, then we can do this. And then the final point is to how you would incorporate this into the GDS. And the proposal is to add it as an extension or / an annex to accommodate these multi-category surface temperature products. And one of the reasons to do this is so that GRIS keeps its focus on SST, and we're not seen to be trying to dictate to the global surface temperature community on formats. Of course, should this be applicable to other multiple surface temperature products, then that might be useful, but we should do this in a way that we still keep the focus on SST. And the idea is the annex would just have be an exact replica to a certain extent of what is in the main GDS, and it would only include the deltas that you need to consider when you generate one of these multi-surface temperature products. So I think apart from the passive microwave name definition, and then the single surface temperature, at least at level 2, I don't think there's anything controversial for those that have contributed so far. And I'd like to acknowledge in particular Steiner and colleagues at DMI and Chris for their feedback so far, which has been very useful and being able to put this together. And with that, yeah, if there's any questions.
Okay, one comment from Chris.
Thanks, Gary. You mentioned LST. I'm not sure whether you're referring to land or lakes. I would comment that in GRIST over the years, we have had work on inland waters, and we should, at the same time as handling the IST, explicitly acknowledge that we also cover inland waters, so lake surface water temperature in some way. But it looks like this plan can naturally extend to that as well.
Yeah, thanks, Chris. Good point. Yeah, in this particular case, it is land surface temperature. But yeah, no, I agree with you. And yes, it can be expanded to however many sort of categories we think. And yeah, inland waters is an extremely important one. So the same principles could be used.
Okay, so if there are not any more comments, so we can move to uncertainties with a summary of by Owen of what is proposed.
So this is basically summarizing the presentation I showed you earlier, but talking about uncertainties. So the proposition here is that we want to add specifications of how we do the uncertainties. The core metadata should follow the CF conventions proposal we're working on. So as I said earlier, basically for the main sea surface temperature variable, you list the associated uncertainties with a new attribute. And which lists the different uncertainty variables, and you've got the error correlation attribute metadata on the uncertainty variables to specify what type of uncertainty you have there. From the GDS side, the main thing we want to do is specify a standard set of uncertainty components that people can provide. So the primary total uncertainty would be sea surface temperature _ uncertainty, and all data sets would be required to provide this. And this is in effect a replacement for the current SSCS _ standard deviation. In the case of level 2 and level 3, you could provide, say, independent, correlated, and common uncertainties. So we would recommend 3 standard names for these, which anyone can use. Depending on how your retrieval works, if you've got a correction to a depth, you may also want to add things like uncertainty correlated depth adjustment. So those would be optional, and you can fill them in as is appropriate for your data set. Any questions or comments on the uncertainty components? Chris?
So just to make it clear, if a data producer currently only produces an uncertainty estimate via an SSES method, they can still keep doing it that way, but it won't be called an SSES anymore. So you don't have to, it's not implying they have to change the method of their uncertainty estimate.
Yes, correct.
But if you have a bottom-up one, for example, like yours, you
Yes.
still put it in the same field. It's just generated as you prefer to generate it. So
yes, if you have a method that's basically the SSCS standard deviation, you can continue to use that and just call it put it in the total uncertainty field. If you've got a way to, say, for instance, propagate your radiometric noise through your retrieval and estimate the random component, then you can store that in the uncertainty _ independent, but those are all optional. Yeah.
Yeah, and so my question is, for those providing the other recommended uncertainties, my question is, the sea surface and temperature uncertainty would be the total uncertainty, so will them sum up in a quadratic way, in a way?
So I didn't catch the end.
Yeah, so since that's what is related of Chris' comments, that what we are saying is that the sea surface temperature uncertainty should replace, in a way, to the producers that are providing this standard deviation right now.
Yeah.
So my question is, the other independent uncertainties that you are related here that are recommended, should they sum up to the total, to the first one?
Yes.
So in a quadratic way, that's it.
Yes. So if you switch to a new method and do it bottom up, then you provide your independent uncertainty and your other components, and then you add them in quadrature to get the total.
So are you okay? But what if someone knows how to do the noise part but doesn't know how to separate the other two parts? And so you're actually going to insist that if you have any knowledge of components, you can only add these if you know how to do all of them and add them up to the right total.
Well, if you know the total and you know how to estimate one of the components, you could subtract that one component.
But you're still left with a combination of all the other components.
Yeah. Yeah, so you could have the total, the uncertainty independent, and then uncertainty other.
Right.
So,
okay, so
these are, you can have as many components as you wish.
But if you're having them, they should combine in quadrature to the total. That's the, okay.
Yes.
That's a good clarification.
So, case study. So modeler is using for years and years some L2P product which has SES standard deviation. Now new satellite come up with some, let's say from your side, and it has sea surface temperature uncertainty in it. How that person is going to know it's the same SES standard deviation and sea surface temperature uncertainty.
So I'm assuming that you'll have your SSESs in the GDS version 2 files.
Yeah.
So it would always be, if it's a version 2 file, you've got the SSESs. If it's a version 3 file, then it's got the uncertainty variables.
Yeah, but isn't that too complicated for the users? Means, what I mean, we can do other way around also, right? In the new file, you can still call it as a SES standard deviation, and in the comment, you can say it's not done with SES, it's the uncertainty calculated with whatever method.
But the reason, Pallavi, is that if a CF convention makes this standard everywhere, it's not just going to be the GDS that's doing this. So people should learn about it through all the other things that adopt the CF convention. So I think it's a really wise idea to be aligned with where the CF convention
Yeah,
is
but in that case, we will have to reprocess everything back to make it consistent. Otherwise, until 2026, you are using SES standard deviation, and suddenly you have to jump up.
Well, if you switch the GDS version, that will be the situation. But if you're carrying on making a version 2 GDS product, you don't need to change until you switch to a new version, you know, until you make a new product. So it's not that you would change it halfway through your product stream without changing the GDS version.
Okay, so there is no.
So you carry on as
users.
You carry on as you are, but maybe the next satellite you do it the new way.
Yeah, so this would be brought in with all the other changes that are coming with GDS3. I think Andy was next.
Okay, I see uncertainty here. So is there still going to be an SSES bias in the GDS3?
Next slide.
Okay, fair enough. And the other question is, I see it's in the light of this SST, IST, blah, 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 all these things that we've just seen, where it says sea surface temperature uncertainty, underneath it, is that actually sea surface temperature uncertainty independent and sea surface temperature uncertainty correlated and so on? No, it's not?
So the top one, it's whatever your primary data variable is, underscore uncertainty. So if it's sea surface temperature is your data variable, you have sea surface temperature underscore uncertainty.
Right.
The other ones are just uncertainty underscore something.
Okay. Okay. So it would be something like, well, if it's just if it's surface temperature, then they would just
surface temperature underscore uncertainty. And in this example here, I've called the main variable SST, but in your case, if it's surface temperature, then you'd have surface temperature uncertainty variables equals surface temperature underscore uncertainty. And then list the associated, well, if you have additional components, then you can
associate
there.
Okay, with the primary variable.
Yeah.
Okay.
I shortened the names so it was easier to read on the example.
Looking for the bias one, but is it there? The next slide. Would you mean next slide or one?
So I've got a separate slide to talk about SSES bias, and basically we don't want it.
Owen, a clarification. So I'm a bit tired, so I got confused. But this is taught also for a level 4 SSD product. Otherwise, how can we compute
so
the fields?
The current examples for the components I've taken from the level 2 and 3. If it's a level 4 product, then currently they only have a single value. So what is currently called analysis error or SST error, analysis error, would become sea surface temperature underscore uncertainty. You've only got one component. It is the total. But if there was a level 4 analysis that could calculate uncertainties at different correlation length scales, then it would be perfectly valid for them to have the total and then say uncertainty underscore small scale uncertainty underscore large scale.
Okay, thanks.
I'm a bit confused by the naming thing that Andy raised, because you just said something that seemed to contradict the previous slide. You said the primary components, the components would be just uncertainty independent for the primary variable, but then you said it would be SST underscore uncertainty. I'm just needs to be clear. I don't really mind.
So in this example, the primary variable, the data variable, was called SST. And I only did that so that you could read the text and still have it on a single line. But in practice, the data variable is called, whatever it's called, sea surface temperature. Then the associated total uncertainty is sea surface temperature underscore uncertainty. Was another question from the back? Okay, moving on. So then we have SSCS bias. The main issue here is it's somewhat confusing to end users, and everyone seems to use it in a different way. Sometimes it's an adjustment to go from skin to depth. Sometimes it's bias correction due to an inherent retrieval biases, and sometimes maybe it's something else. So our proposition is that SAS bias is retired and will not be allowed in GDS3 files. If the SSCS bias was an adjustment to correct a bias in the retrieval, then it's now the data producer's job to apply that bias correction to the data in the file before they provide it to end users. So there'll be no more, you open up your file, you read sea surface temperature, and you add this bias parameter for the data. The end user, they just open the file and use the data. Second case, if SSCS bias was an adjustment to go from skin to depth or buoy or whatever, then now the preferred method is just to add a second variable such as sea surface temperature underscore depth. So that way your file would contain two SST variables, the skin one and the depth one. They have different names, but both of them, you just use them as is, and you don't have to add adjustments to them. Because you've got two different variables, you'd also have two different total uncertainties. So sea surface temperature uncertainty for the first one, and sea surface temperature depth underscore uncertainty for the second. And each variable can have separate components. It's also perfectly valid for one component to be used by both variables. So if your radiometric noise is the same for both, then your underscore uncertainty underscore independent will be used in both. And going back to that slide, in this case, for instance, if you had them all split up, your skin one would use the uncertainty independent, correlated and common, and then your depth only SST could additionally have the uncertainty and the depth adjustment. Going back to the SSCS bias, finally, in exceptional circumstances, if you're using your bias to represent something else, such as it's a bias relative to in situ that most data users should not be adding, so it's there to provide some additional value, but it's not supposed to be added to the SST data most of the time. You could add an optional variable such as adjustment underscore whatever you're adjusting to. So here's an example where you might have adjustment underscore in situ, and it's you should have the comment and references attribute to explain what it is and when, why, and when it should be used, and links to some online documentation to explain how it was calculated and so on. Andy, does that answer your question?
Yes. However, I would say that more people use SSES bias than use SSES standard deviation. That's my observation.
Do you mean producers or users?
Users. Or let's see, people who ingest L4 data, they choose to ingest with or without the SSES bias. For example, if you take something like Axpo products, the standard global algorithm is essentially, like an NLSST type regression, but then the SSES bias is like the piecewise regression, or at least it is in version 2.8 and 3.0. The trouble with using that is that though it does reduce the bias and reduce the standard deviation a little bit, it also reduces the algorithm sensitivity to fronts. And so being able to turn it off and turn it on is very, very useful. And if someone's come up with a better bias correction, then it's nice to be able to remove that, remove the old one and put something new in. And if you've embedded it into that product, you cannot take it out again.
Well, it sounds like you've got a case where there's two different retrievals. So you would store that as two different sea surface temperatures. You might have sea surface temperature for your standard non-linear one, and then an alternate sea surface temperature underscore piecewise.
Yeah, right. Okay. So you could do something like that, but I'm just saying that if you've got corrections that you apply, let's say, for example, I've got an altimeter data because this is a CF standard that's going to apply to all sorts of data, and you're using I'm applying a wet tropospheric correction of blah from this model, and you've got a whole bunch of things, and then someone comes up with a new model or new ionospheric correction or something like that. You can just take that one out and put a new one in without having to go back and reprocess the entire data set. So I'm not. Yeah, yeah.
This is so you want the third case then, where it's stored as an adjustment. So you have adjustment underscore piecewise or adjustment underscore Andy's new method.
You could do that. As so, but basically I'm just saying that's how SSES bias is used by people.
Yeah. But SSES bias limits you to only one, and you've just given an example where you might want two different adjustments.
Yeah. So what you're saying is that we come up with a new field, get rid of the old one. So people shouldn't worry about it because we're eliminating the term SSES completely. And if you want to have some other corrections, you just have to add them in. Is that?
Yes.
Yes. Okay.
John.
Not really related with just being talked about, but I think it would be good if there was an enforced comment or enforced method, because if someone has derived their uncertainty from matchup database, that's kind of a top-down methodology which has potentially a particular distribution of uncertainty associated with it. And if you do a bottom-up one, it potentially has a different uncertainty characteristic, and it would be nice if people knew which one you'd used in the data.
Yes.
I think.
So in the CF proposal, there's some allowance for using some optional attributes in specifying that. But yeah, if we want to make it more, if we want to make it a required thing in GDS, we maybe need to, add more here.
I mean, you just add a bit of metadata just to say where your uncertainties it came from, or give a reference or whatever. Because as people get used to the uncertainties, they're going to begin to understand the differences between the different ways of doing it, and they may find that important. Hopefully, they will find it important.
Yes.
Okay, so there are a few additional things. So ancillary fields, so in particular environmental variables. So there was already a list of mandatory and optional fields. So something was missing, like a total water vapor content. So we propose to add this also as a mandatory variable. Sea ice fraction also is a mandatory, except for datasets that do not cover sea ice. So then clouds. So this is more something for a future iteration, because there are some producers are providing variables like the probability of cloud coverage. So this is something that may be considered also and harmonized, so that more producer can put this information into their data set. But there was no discussion about this in this year, so we keep this for a possible addition in a future iteration. Then there is the case of ultra-high-resolution sea surface temperature, and so we need to address what are the specific issues related to this kind of ultra-high-resolution data. So there are issues related to the geolocation accuracy and uncertainty, the compression of lateral that I've mentioned before. We could consider also adding a more advanced surface tip flag in order to address more surface types like rivers and tidal zones and so on. So maybe a better description of this. Possibly also the combination of lake, land, river surface temperature. So it's more or less the same discussion like for with IST. Also, many ultra-high resolution imagery are provided in UTM as a UTM tile, so in UTM projection. So is it something that should be the way to go for SST as well? So it is a plan in the coastal ultra-resolution SST task team to provide suggestions and evolutions to the GDS regarding all these specificities. But this task team has not yet fully started. So this is we are not in position now to get inputs that can be written on in the first GDS 3.0 version, but again, this is something that will enrich a later version. A minor thing about the file quality attribute that was not really said by many users so far, and the description of this was a bit ambiguous. So we propose a better description of this attribute and the values that you should put in this. So this is the new list of possible values. So 0 file quality control failed for some reason. 1 will be for files that were generated but are unusable because they are no valid data or they are fully clouded, things like this. 2 is reserved for non-satellite problems or periods of the lifetime, like the commissioning phase of a mission. And 3 is, as before, for good data. Why?
Well, sorry, I didn't mean to interrupt. I'm just thinking you've got lists of possible problems, but you might want to change that list. And if good data is your ultimate thing, why don't you put good data as 0? But that would be changing your whole industry.
Yeah,
So
because this
you
was
don't wanna do that.
ranking we had so far, so we don't change this. Yeah. Okay. Also, since there were many new versions of CF convention since last time we aligned with it in the GDS, so we need also to review all this evolution and extend its usage for all the new features that have been introduced in CF convention. So there will be some additions related to that to better align with the latest version of CF conventions. Then there are some requirements from this CEO's analysis ready dataset. So maybe Ed, you want to get over this. So here again, we are trying to align the different format requirements.
Well, I've been participating in a few telecons. There's a group within CIOS that is developing the product family specification for surface temperature. So within the GHRSST ARD model, you produce a product family specification for the measurement of interest. So there's been one generated for SAR and aquatic something or another. So they're doing it for surface temperature, and I participated. I did a little mapping or presented a little mapping of the GDS2 structure and how it compared to the ARD. And then another guy took my work and took a little bit deeper dive. And this is kind of what they found with regards to where we're not overlapping with their specification, and might be useful that we do try to make an attempt in this new GDS specification to, as best we can, be CIOS ARD compliant. We might, have some dividends down the road. Okay, so what did this gap analysis showed? I guess one of the things that's missing consistently a CRS variable. Machine readability, I think the author interpreted it wrong. All our metadata is CF ACD compliant as is, so it is machine readable. He's wrong on that count. But then there's other things. We don't make any effort to document algorithms specifically in our metadata model, at least not in a kind of consistent way. And then the other thing is solar viewer geometry is just optional. It's not mandatory, and they're looking at it to be mandatory in their specification. They also have a field for saturation, where one or more of the input spectral bands are saturated. I don't know, is that really germane to thermal AR and microwave? Do we ever have sensors that saturate? Maybe, I don't know. I mean, that's more for like optical stuff or like, I don't know. Okay. But we don't have anything for saturation. We don't carefully document atmospheric corrections, and we don't deal with the geometric accuracy. I think we talked about that a little bit in some of our proposals that we want to improve that. Whereas the pixel center and other attributes of geometric accuracy. So if we could, in these GDS 3 evolution discussions and implementation, address some of these, I think that would be good for us down, because then we could propose that we are CF ARD compliant, or write our own product family specification just for surface water temperature. And I think that would be good. So,
but I think some of these are really coming from reflectance-driven work. I mean, the solar and viewing geometry has to be taken into account when you're driving an SST, but you don't want to bloat your files for SST with that information, I would think. It doesn't seem necessary for a thermal product.
Okay.
Geophysical product.
The surface temperature guys that are more land, these are the guys mostly land driven. They also want to do ice temperature. That's what they say they need. They want.
It's not really. Well, I might be. So the viewing geometry may affect the uncertainty, and the data producer should have reflected that in their uncertainty field, but it's not really going to affect how you use a temperature.
Yeah.
Well, after the fact. Similarly with saturation, there are thermal channels that saturate. That's true.
Yeah.
But the data producer shouldn't have used them. or they should have switched to another algorithm if they need to avoid such a channel. And again, that would be reflected in the uncertainty. So I'm not sure that that's as relevant when you're looking at a temperature either.
What about the saturation?
Well, that's what I was saying. There are channels that saturate, but when they're saturated, you're not using them for a temperature anymore. Or you shouldn't be anyway.
Please use the microphone, otherwise people are online. I'm sorry, but I need to keep the meeting in a hybrid mode.
I was just thinking that I've seen products that come out the door that just, you don't know how bad they are once they hit that cutoff. So is there a number? Would you just put a number there that say anything above this is, you don't know what it is? No. Yeah, so that's how
I think they're proposing like a variable that pixel by pixel that would tell the user where, the observation is saturated.
I do like that.
I
do like the idea of the algorithm sequence. I think that would be useful.
Yeah, I mean, the saturation thing is relevant at level 1, but not really at level 2.
Well, in any case, this cross-analysis is an ongoing activity, so we may sort out later what we should keep or ignore in what they suggest. But again, that will come for a later version. Okay, then there was also in GDS-v2 a section about regrading, so we are not sure that many people use it, and if it is something that should be revised. So we may discuss this also because there were in previous GRIS meetings, there were many presentations or posters about the regrading issue. So there may be some recommendations that we could come with and include in the GDS in a later version. So just to keep that in mind. So last, I just remind you of this GRIST format checker that exists now. Of course, it's for the version 2 GDS, and that will be upgraded in order to match the GDS v3, and maybe also include these controls about the internal fitness of the datasets to the recommendations for chunking and so on. And this is really my last slide this time. So I remind you also of this open search endpoint for GRIS dataset that allows granular discovery. So it's not yet very well advertised on the GRIS website, but we will be working on make it more accessible and visible from the users. But also we already discussed this last year. OpenSearch is being dropped by many provider and agencies now because there is a new standard, which is a stack, which provides the same kind of search capability. So in the RGTS architecture document, we will recommend to implement a stack as a service for the granular discovery. And this will replace this OpenSearch API. So Stack is anyway is more standard than OpenSearch was. There is a lot more support software to implement this kind of service. It's more. It's also easier to federate the different API from the different providers and to integrate them in a portal. And therefore it provides better interoperability. So this is a move that we want to do with respect to this service of the RGTS system. And that was the last one.
I have a general question, which is whether we're in some sense having to wait for the CF convention people, or are we just doing this on our own timescale?
But I understood that this CF extension for uncertainties will be discussed like in fall or from September, if I read correctly. So it's more or less in line with the targets that we have for the GSV3. So hopefully we can include that in this first release.
Can I just ask about the associated documentation that will have to go with this, in the sense of, for example, we're adding in uncertainties. The use of uncertainties is still not a completely common. Everyone knows, and everyone knows what to do with them. So there will have to be associated document, even at the level of explaining what an uncertainty is in this context. And my other question is that there used to be data readers provided, and I'm wondering if that needs to come back again, given that you're now talking about tie point interpolation, extrapolation for the lat long for the compression. And I know it from my own experience that different level 1 providers provide tie points, but the algorithm that you use to do the tie point can be different between different producers. So we either need to fix on one and have it documented, or well, it needs to be documented or demonstrated. So I'm wondering if you've thought about the fact that when you start putting in things like tie points, you need to tell people how to do the reconstruction correctly.
Yeah. So we will put some guidelines in the GDS. And I think it will be nice also to add some code snippets like Ed just shown for the setting up this cloud optimized NetCDF for data in order to help users to implement this easily. And for the uncertainties, there was all the requirements in GRIST, which was to provide the way you produce your SSCS statistics, and you were supposed to provide them to the project office, and they were supposed to be displayed on the GRIST website. So I think this is more or less the same issue, and that we should encourage the producers to describe.
But I mean, some people never did. And I'm wondering if you therefore shouldn't make it a requirement when you, for example, have the uncertainty that at least for one element, or probably for the top level of uncertainty, it's enforced to provide a reference where people can find the information, and that would enforce the documentation for all different producers to then link back to what they mean by it.
Yeah.
And that could also be part of the checker. The checker checks that the web address or whatever actually works.
Yeah, it could be a way to encourage people to have this reference attribute as a mandatory. But
okay, any further comments? So shall we close the session here? I don't know if you want to wrap up, say something else, because we have another meeting now. We are late.
If no one's making, I just want to thank everyone who's worked on the GDS3 preparation. It's a lot of detailed stuff. It's been a very good discussion. I'm glad that there seems to be at least, well, there's support expressed through silence. And I think that's a testament to the quality of the thinking that's gone on and what's been presented. So thanks very much. And I think we should give those guys a bit of applause.
That's all, you are free. Part of you, not everyone. So the AC meeting starts in 5 minutes. So just quick restroom pause and we go.